0836. Right now, somewhere above your head, a beam of light is crossing the entire continental United States in the time it takes a single neuron in your brain to fire. Not the time it takes you to blink. Not the time it takes you to react. The time it takes one electrical signal to jump across one microscopic gap between two nerve cells. In that same fraction of a second, light has already traveled from New York to Los Angeles and back again, twice. This is not a metaphor. This is not an approximation designed to impress you. This is the measured, verified, reproduced to 11 decimal places reality of the universe you inhabit. Light moves at 29979 kilometers per second, every second, without exception, without variation, without the slightest deviation, regardless of who is measuring it, where they are standing, or how fast they themselves are moving. But here is what most people never stop to consider. The speed of light has almost nothing to do with light. That single statement contains more physics than most textbooks manage to convey across hundreds of pages. The number 29979 kilometers per second is not a property of photons, the way mass is a property of protons, or charge is a property of electrons. It is something far more fundamental than that. It is the speed at which cause produces effect. It is the maximum rate at which the universe can communicate any piece of information to any other part of itself. It is the tempo at which reality updates. Photons travel at this speed, not because they are special, but because they happen to be massless, and massless things have no choice but to travel at exactly this rate. Remove the photons entirely, and the speed limit remains. Burn every star in the cosmos to darkness, and the limit persists. It existed before the first photon ever flickered into existence in the universe's earliest moments, and it will remain long after the last one fades into the cold silence of maximum entropy. What Richard Feynman eventually discovered about why this limit exists will fundamentally alter the way you understand the nature of physical reality. It will show you that this barrier is not a wall preventing motion. It is a structural feature of existence itself, a feature so deep, so woven into the fabric of space-time and quantum mechanics simultaneously, that asking how to exceed it is not like asking how to run faster. It is like asking how to find a point north of the North Pole. The question assumes something that simply does not exist. But we are getting ahead of ourselves, because before Feynman, before Einstein, before any human being had the mathematical tools to understand why this limit exists, there was first the far simpler and far more humbling problem of proving that it existed at all. And that story begins on a hillside outside Florence with a lantern, an assistant, and an old man's impossible ambition. If you find yourself drawn to journeys that reach into the deepest structure of reality and come back changed, do me a small favor and hit that like button and subscribe. It genuinely helps this channel continue making content like this. Now find somewhere quiet and comfortable. What follows will take everything you think you know about space-time and the nature of existence and rebuild it from the ground up. Let's begin. Galileo Galilei climbed that hillside in 1638 as a man already defeated by the world. He was 74 years old. The Inquisition had forced him to recant his support for the Copernican model of the solar system 5 years earlier. He was under house arrest, forbidden from publishing, his eyesight failing. The universe he had spent his life illuminating was slowly going dark around him, yet his mind had not stopped moving. The question that occupied him on that hillside was deceptively simple. How fast does light travel? Not whether it was fast, not whether it was faster than sound. The specific, numerical, measurable velocity of a beam of light crossing a given distance in a given amount of time. No one had ever measured it. Many philosophers had assumed light was instantaneous, that it required no time whatsoever to travel from source to eye. Galileo suspected otherwise, and he designed what seemed on paper like an elegant solution. He stationed himself on one hilltop with a shuttered lantern. His assistant waited on a second hilltop in the distance, carrying an identical lantern with instructions memorized and timing rehearsed. The method was straightforward. Galileo would uncover his lantern. The moment his assistant saw the flash across the valley, he would uncover his own lantern in response. Galileo would then measure the delay between his outgoing flash and the returning signal. Divide the round-trip distance by the elapsed time. The result would be the speed of light. The logic was sound. The execution was careful. The result was devastating. Nothing. No delay whatsoever. No matter how far apart they positioned themselves, no matter how many times they repeated the procedure, the returning flash appeared instantaneous. Light seemed to cross any earthly distance in 0 time. Galileo tried greater separations. He recruited assistants with faster reflexes. He refined his timing methods until they were as precise as 17th century technology allowed. Every attempt produced the same maddening result. The response always appeared immediate. The delay, if it existed at all, was too small to measure. Galileo drew the only honest conclusion available to him. Either light traveled infinitely fast, or it moved so quickly that no human instrument could detect its transit time across the distances available to him on Earth. He suspected the latter. He could not prove it. He was right, and his failure was not a failure of ingenuity. It was a failure of scale. Consider the mathematics of what he was attempting. Light travels at approximately 29979 kilometers per second. Across a valley of, say, 1 kilometer, a round trip of 2 kilometers light takes roughly 0.0000067 seconds to complete the journey. 6.5 microseconds. Human reaction time, even for the fastest trained subjects under ideal conditions, measures approximately 15,000,000 microseconds. Galileo was attempting to detect a delay 0.6 of a microsecond using instruments with a precision of 15,000,000 microseconds. The signal was buried under a mountain of noise, so vast it might as well not have existed. To measure light speed, you needed distances so enormous that the accumulated delay became detectable. You needed not hills across a valley, but distances spanning a significant fraction of the solar system. You needed to wait not for a human assistant to respond, but for a celestial object to complete a predictable orbital event that could be timed against a calendar calculated months in advance. You needed, in short, to stop looking at Earth and start looking at Jupiter. Ole Rømer arrived at the Paris Observatory in 1672 as a young Danish astronomer with sharp eyes and a methodical mind. He was 25 years old, trained in mathematics, and assigned a task that seemed almost clerical in its routine. He was to observe and record the orbital motions of Jupiter's innermost large moon Io, discovered by Galileo himself 70 years earlier. Specifically, Rømer was to track the timing of Io's eclipses, the moments when the moon disappeared into Jupiter's enormous shadow, and the moments when it emerged on the other side. Astronomers at the time used these eclipses as a cosmic clock. Io orbits Jupiter with extraordinary regularity, completing one circuit approximately every 42.5 hours. If you recorded enough eclipses, you could predict future ones with great precision, and those predictions could be used as reference points for navigational calculations. Ships could determine their longitude by comparing local time with the predicted time of a Jovian eclipse. The practical applications were enormous. Rømer began recording. Month after month, eclipse after eclipse, he built a table of observations more detailed than any previously compiled. And somewhere in that growing table, he noticed something that should not have been there. The eclipses were drifting. When Earth's orbit carried it toward Jupiter during the first half of the year, the eclipses occurred slightly earlier than his tables predicted. When Earth's orbit swung it away from Jupiter during the second half of the year, the eclipses arrived slightly late. The cumulative discrepancy across the full diameter of Earth's orbit around the Sun accumulated to approximately 22 minutes. 22 minutes of unexplained deviation from a celestial clock that was supposed to be among the most reliable in the solar system. Other astronomers attributed the drift to imperfections in their models. Perhaps Io's orbit was slightly irregular. Perhaps Jupiter's gravity introduced subtle perturbations. Perhaps the calculations themselves contained small accumulated errors. These explanations were reasonable. They were also wrong. Rømer sat with his data and considered an entirely different interpretation. What if Io's eclipses were occurring exactly on schedule? What if the deviation was not in the moon's behavior, but in the light carrying news of that behavior to Earth. When Earth was closer to Jupiter, the light announcing eclipse had less distance to cross and arrived sooner. When Earth was farther away, the same light needed more time to bridge the expanded gap. The 22-minute discrepancy was not a clock malfunction. It was light travel time across the diameter of Earth's orbit. This meant light had a finite speed. Not merely fast, not merely very fast. A specific, measurable, finite velocity that required real time to carry information from one point in the solar system to another. In 1676, Romer announced his interpretation to the scientific community of Paris. The reaction was divided. Some recognized immediately the revolutionary nature of the claim. Others remained skeptical, preferring imperfect orbital models to the radical conclusion that light was not instantaneous. The debate would not be fully resolved for decades. Romer attempted a calculation. Dividing the diameter of Earth's orbit by the accumulated time delay, he arrived at approximately 2,000,000 kilometers per second. This estimate was roughly 26% lower than the value we accept today. The error was understandable. The precise diameter of Earth's orbit around the Sun was not yet well established in 1676. His timing measurements, however, carefully contained small accumulated uncertainties, but the magnitude of his achievement dwarfed these imperfections entirely. Romer had proven something no human being had ever demonstrated before. Light was not instantaneous. It traveled at a specific velocity. Information about distant events required real time to reach observers. And this meant something that would take centuries to fully appreciate. When you look at Jupiter in tonight's sky, you are not seeing Jupiter as it is. You are seeing Jupiter as it was roughly 35 minutes ago, depending on where both planets sit in their orbits. The light reaching your eyes left that world more than half an hour before it arrived at your retina. The Jupiter you see does not exist yet. It is a memory, a fossil of a moment that has already passed, preserved in the electromagnetic radiation racing toward you across empty space. This is not a curiosity. It is a fundamental feature of the universe. Every observation is a look backward in time. Every distant object we see is a ghost of what once was. The farther the object, the older the ghost. The sun we see is 8 minutes old. The nearest star beyond our sun is 4 years old. The Andromeda galaxy, visible on clear nights as a faint smear of light, shows us a version of that galaxy as it existed 2.5 million years ago. The beings living there now, if any exist, are looking back at us across the same abyss, seeing the Earth of 2.5 million years ago, when our ancestors had not yet discovered fire. Romer's measurement changed everything, but it raised a question that would haunt physics for the next 2 centuries. If light has a specific speed, what determines that speed? What is light actually doing as it crosses the void between worlds? What medium does it travel through? And why does it travel at this particular velocity rather than some faster or slower value? These questions seemed straightforward in 1676. The answers, when they finally came, would shatter the foundations of classical physics and reveal something far stranger than anyone had imagined. The first step toward those answers required physicists to understand what light actually was. And that understanding, when it arrived in the mid-19th century, created a crisis that demanded a resolution no one was prepared to accept. The trouble with light, as physicists in the 19th century understood it, was that it behaved exactly like a wave. This was not a casual observation. It was a conclusion supported by decades of careful experimentation, mathematical analysis, and theoretical development. Thomas Young demonstrated it in 1801 by sending light through 2 narrow slits cut into an opaque barrier. The light emerging from the 2 slits spread outward and overlapped, and where the overlapping waves aligned, they reinforced each other into bright bands. Where they opposed each other, they cancelled into darkness. This interference pattern, stripes of light and shadow, alternating with mathematical precision, was the unmistakable signature of wave behavior. Particles do not interfere, waves do. Light interfered. Therefore, light was a wave. Augustin Jean Fresnel confirmed and extended Young's findings through the 1810s and 1820s, developing a comprehensive mathematical theory of wave optics. that predicted the behavior of light passing through apertures around obstacles and through optical instruments with extraordinary accuracy. Phenomena that had puzzled scientists for generations, the bright spot appearing at the center of a circular shadow, the colored rings surrounding points of contact between curved glass surfaces, the precise patterns of diffraction around sharp edges, all of them fell into perfect agreement with the wave theory. The evidence was overwhelming and converging from multiple directions simultaneously. James Clerk Maxwell completed the picture in 1865. Maxwell was a Scottish physicist of unusual mathematical gifts and physical intuition. Working in his study at Glenlair, his family estate in Scotland, he unified electricity and magnetism into a single coherent mathematical framework now called Maxwell's equations. These 4 compact equations described every known electromagnetic phenomenon with perfect precision. But they did something more than describe existing observations. They predicted something entirely new. Maxwell noticed that his equations permitted a particular type of solution, a self-sustaining wave in which an oscillating electric field generated an oscillating magnetic field, which in turn regenerated the oscillating electric field, which regenerated the magnetic field, the two fields perpetually recreating each other as the wave propagated forward through space. When Maxwell calculated the speed at which this electromagnetic wave must travel, he obtained a number from the fundamental constants of electricity and magnetism that appeared in his equations. The number was 299,792 kilometers per second. Maxwell stared at this result and recognized immediately what it meant. The speed predicted by his equations for electromagnetic waves matched the measured speed of light with extraordinary precision. This could not be coincidence. Light was an electromagnetic wave, not metaphorically, not approximately, literally. A beam of light was a self-sustaining oscillation of electric and magnetic fields propagating through space at the speed his equations demanded. This was one of the greatest unifications in the history of science. Optics, electricity, and magnetism, 3 previously separate branches of physics, collapsed into a single framework. And Maxwell's equations predicted something even more remarkable. Electromagnetic waves of any frequency should exist and should all travel at the same speed. Radio waves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays, all manifestations of the same phenomenon, differing only in the frequency of their oscillation, all traveling at exactly 299,792 kilometers per second. Heinrich Hertz confirmed the existence of radio waves experimentally in 1887, precisely as Maxwell's equations predicted. The theory was correct, the unification was real, but success created a problem. Waves require a medium. This was not a philosophical preference or an arbitrary assumption. It was a physical necessity grounded in the deepest understanding of what waves actually are. A wave is a disturbance propagating through something. Ocean waves are disturbances propagating through water. Sound waves are disturbances propagating through air or through solids or through any material substance. Remove the medium and the wave cannot exist. You cannot have ocean waves without an ocean. You cannot have sound in a perfect vacuum. The wave has nothing to wave through. Light was a wave. Therefore, light required a medium. The medium was given a name, the luminiferous ether. Luminiferous meaning light-bearing. This invisible substance was imagined to permeate all of space, filling the vast empty distances between planets and stars, providing the substrate through which electromagnetic vibrations could propagate. The ether had to have extraordinary properties to accommodate what physicists knew about light. It had to be extraordinarily rigid, because the speed of a wave through any medium depends on that medium's stiffness, and light traveled at enormous speeds, requiring enormous stiffness. Yet the ether had to be completely transparent and offer essentially no resistance to the motion of planets and other massive objects moving through it, because no such resistance had ever been observed. It had to be simultaneously the stiffest and the most tenuous substance imaginable. These properties seemed contradictory. Physicists acknowledged this tension but pressed forward regardless, because the alternative was worse. The alternative was waves without a medium, and that, in 1880, was simply inconceivable. If the ether existed, it had to be stationary, or at least it had to define a preferred reference frame, a cosmic rest frame, against which all motion could in principle be measured. And if it defined such a frame, then Earth's motion through the ether should be detectable. Consider the situation carefully. Earth orbits the Sun at approximately 30 kilometers per second. As it moves through the stationary ether, it should experience an ether wind analogous to the wind you feel when you run through still air. This ether wind should affect the apparent speed of light measured in different directions. Light traveling in the direction of Earth's motion through the ether would effectively be moving against a headwind, appearing slightly slower relative to Earth. Light traveling opposite to Earth's motion would have a tailwind appearing slightly faster. Light traveling perpendicular to Earth's motion would be unaffected. The expected difference in apparent light speed between these directions was small, roughly 1 part in 10,000, reflecting the ratio of Earth's orbital speed to the speed of light. But late 19th century precision instruments could detect such differences. The technology existed, the calculation was clear, the experiment was straightforward in principle, and Albert Michelson was the most precise optical experimenter in the world. Michelson had already devoted years of his life to measuring the speed of light with ever-increasing accuracy. He had developed rotating mirror techniques of extraordinary refinement, achieving measurements accurate to within a fraction of a percent. He had won international recognition for this work. Precision was not merely a professional skill for Michelson. It was a personal obsession, a form of devotion to the idea that the universe could be known exactly if only the measurements were careful enough. In 1887, he joined forces with Edward Morley, a chemist at Case Western Reserve University in Cleveland, Ohio, who brought complementary experimental skills and equal dedication to precision. Together they designed and built the most sensitive optical instrument ever constructed to that point in history. The Michelson-Morley interferometer split a single beam of light into 2 perpendicular paths using a half-silvered mirror, a piece of glass that reflected half the incoming light and transmitted the other half. One beam traveled parallel to Earth's orbital motion. The other traveled perpendicular to it. Both beams bounced off mirrors positioned at equal distances and returned to recombine at the half-silvered mirror. If the 2 beams experienced different effective light speeds due to the ether wind, they would travel their equal distances in slightly different amounts of time and would arrive back slightly out of phase with each other. When 2 light beams combine out of phase, they create an interference pattern of alternating light and dark bands. The spacing and position of these bands would reveal precisely how much the 2 beams had diverged in travel time, which in turn would reveal the speed of Earth's motion through the ether. Michelson and Morley mounted their entire apparatus on a massive stone slab, roughly 1.5 meters square, floating in a circular trough of liquid mercury. Mercury reduced friction to near zero, allowing the entire apparatus to rotate smoothly without vibration. By rotating the interferometer slowly and continuously, they could observe whether the interference pattern shifted as different arms of the instrument aligned with and against the ether wind. If the ether existed, the pattern would shift with each rotation, revealing the ether wind's direction and magnitude. The precision of their instrument exceeded the theoretical requirements by a comfortable margin. If the ether wind existed at the magnitude their calculations predicted, the resulting fringe shift would be unmistakably visible. They were not looking for a needle in a haystack. They were looking for a lighthouse in a dark field. The signal should have been obvious. They measured in the morning and in the evening when Earth's rotation carried the apparatus in different directions. They measured in different seasons when Earth's position in its orbit pointed toward different regions of the sky. They rotated the apparatus continuously and watched for any pattern in the fringe positions. They repeated everything. They checked their calibrations. They eliminated every source of systematic error they could identify. The interference pattern did not shift. Not by the expected amount, not by half the expected amount, not by 1/10. The fringes remained essentially stationary regardless of the apparatus's orientation, regardless of the time of day, regardless of the season. The result was so far below detection threshold that the only honest conclusion was that the effect was absent entirely. There was no ether wind, which meant either the ether somehow moved with Earth dragged along perfectly, despite being the medium through which Earth moved, which made no physical sense and contradicted other observations, or the ether did not exist. The luminiferous ether, the logical necessity that every physicist in 1887 accepted as essentially certain, had simply failed to show up. Michelson was devastated. He had designed the experiment expecting to measure something to add a new precise value to the catalogue of physical constants. Instead, he had measured nothing, and nothing was somehow worse than any finite result he might have obtained. He called the experiment a failure. History would eventually recognize it as one of the most important experiments ever performed, not because of what it found, but because of the crisis it created. The null result of the Michelson-Morley experiment threw theoretical physics into genuine disarray. The wave theory of light was overwhelming in its experimental support. Waves require media. Therefore, light required a medium, yet the medium appeared not to exist. These three statements could not all be simultaneously true, and every attempt to reconcile them produced new contradictions. Hendrik Lorentz, a Dutch physicist of remarkable mathematical ability, proposed one rescue attempt. Perhaps objects moving through the ether contracted slightly in the direction of motion, he suggested. This length contraction, if it occurred in exactly the right proportion, would cause the two arms of the Michelson-Morley interferometer to change length in precisely the way needed to compensate for the ether wind effect. The arm pointing into the ether wind would shorten, making that beam's journey slightly shorter, compensating for its reduced apparent speed. The null result would then be explained without abandoning the ether. Lorentz developed the mathematics of this contraction precisely, and found that it required an arm to shorten by a factor equal to what we now call the Lorentz factor, a quantity that depends on the ratio of the object's velocity to a speed of light. George Fitzgerald had independently proposed the same contraction somewhat earlier. The contraction worked mathematically. It reproduced the null result. But it felt wrong in the way that all rescue hypotheses feel wrong when they exist solely to protect a theory from its own failure. Why would matter contract when moving through ether? What physical mechanism caused the contraction? Lorentz tried to derive it from electromagnetic interactions between the ether and matter, but the derivation required additional assumption that themselves required justification. The explanation expanded to fill every gap with new assumptions, none of them independently motivated. The ether theory was accumulating epicycles. Henri Poincaré, the French mathematician and physicist, understood more clearly than most of his contemporaries how deep the crisis ran. He pointed out that the Michelson-Morley result suggested something disturbing about the nature of motion itself. Perhaps he speculated it was fundamentally impossible to detect motion relative to the ether through any optical experiment. Perhaps the laws of physics conspired to hide absolute motion from observers in a way so complete and so systematic that the ether itself became undetectable and therefore meaningless as a physical concept. Poincaré was circling the truth. He was seeing the shadow of the answer without yet grasping what cast it. The resolution, when it finally came, would not save the ether. It would dissolve it entirely. And it would come not from the established centers of European physics, not from the great observatories or the famous university laboratories, but from a patent office in Bern, Switzerland, where a young man who could not find an academic position had been thinking about lanterns on hillsides and what it would mean to catch up to a beam of light. The answer he found did not add new physics to patch the failing ether theory. It removed the ether entirely and replaced it with something far stranger and far more powerful. It revealed that space and time were not the fixed absolute scaffolding within which physical events occurred. They were dynamic, flexible, observer-dependent aspects of a unified structure that bent and stretched in response to motion. And woven into the mathematical heart of that structure, as inevitable as the geometry of a triangle, was the speed of light, not as a property of light, as a property of space-time itself. But before that, revelation could be understood, something even more fundamental had to be confronted, because Einstein's answer, revolutionary as it was, still left a question unanswered. His equation showed precisely what happened to space and time as objects approached light speed. They demonstrated with mathematical certainty that reaching light speed required infinite energy. They predicted every relativistic phenomenon that experiments would later confirm with extraordinary precision. What they did not explain was why. Why was spacetime structured this way? Why did this particular speed serve as the absolute limit? Why 299,792 kilometers per second and not some other value? Einstein built the architecture of special relativity on two postulates that he accepted as fundamental. He did not derive them from anything deeper. He could not. The tools to understand why these postulates were true would not exist until quantum mechanics matured into quantum field theory, and a young physicist named Richard Feynman began visualizing reality in ways that no one before him had managed. That understanding is where we are going. But first, we must follow Einstein to Bern and watch him dismantle the ether with nothing more than two postulates and a willingness to accept their consequences all the way to their logical end. 0839. In the spring of 1905, the Swiss Patent Office in Bern, Switzerland, employed a technical expert, second class, whose job was to evaluate applications for mechanical and electrical patents. He sat at a wooden desk in a government building and read through diagrams of proposed devices, checking whether the claims matched the physics, whether the inventions actually worked, whether the ideas were truly novel. The work was routine. The salary was modest. The position carried no academic prestige whatsoever. His name was Albert Einstein. He was 26 years old, and in the spare hours surrounding that routine work, working alone without access to a major research library, without colleagues to discuss his ideas, without a supervisor to guide his thinking, he was quietly dismantling the foundations of classical physics. In a single calendar year, 1905, Einstein published 4 papers in the journal Annalen der Physik. Any one of them would have secured a lasting reputation for any scientist. Together they transformed physics more profoundly than any single year of scientific output in the history of the discipline. One paper explained Brownian motion, the random jittering of small particles suspended in fluid, and proved definitively that atoms exist as physical objects rather than mathematical conveniences. Another explained the photoelectric effect, the phenomenon by which light striking a metal surface ejects electrons, and introduced the concept of the photon, the quantum of light, for which he would eventually receive the Nobel Prize. A third introduced the special theory of relativity. The fourth, a short addendum to the third, contained the equation E equals mc squared. But none of these papers began with a new experimental result. None of them reported a discovery made in a laboratory. Einstein had no laboratory. He had no equipment, no assistants, no institutional resources. What he had was a decade of restless thinking about a question that had first occurred to him at 16 years old. What would you see if you could catch up to a beam of light? The question sounds almost childlike in its simplicity, but Einstein pursued it with a seriousness that most adult physicists would not have applied to such an apparently naive inquiry. If you accelerated until you were traveling alongside a photon at the same velocity, would the electromagnetic wave appear frozen beside you? Would you observe a stationary oscillating electric and magnetic field suspended motionless in space, keeping pace with your motion, like a companion running at your side? Maxwell's equations said this was impossible. The equations that governed all electromagnetic phenomena contained no provision for stationary electromagnetic waves. They described waves propagating at one specific speed. A frozen wave, a wave traveling at zero velocity relative to an observer, was simply not a solution to Maxwell's equations. It could not occur. It did not exist anywhere in the mathematical structure of electromagnetism. Einstein faced a choice that would have paralyzed most physicists. Either Maxwell's equations were incomplete, failing to describe some exotic regime of high-velocity electromagnetic phenomena, or the premise of the thought experiment was wrong. Perhaps it was not merely difficult to catch up to light. Perhaps it was fundamentally mathematically, structurally impossible. Perhaps light always traveled at the same speed relative to every observer, regardless of the observer's own motion. Most physicists in 1905 would have chosen the first option. Maxwell's equations were known to be extraordinarily successful, but surely they were an approximation that broke down under extreme conditions. Surely at very high velocities, new physics would emerge that modified the predictions. This was the conservative choice, the modest choice, the choice that preserved the intuitive framework of absolute space and time that Newton had bequeathed to physics 2 centuries earlier. Einstein chose the second option. He accepted Maxwell's equations as exact. He accepted that light always traveled at the same speed relative to every observer. And then he followed that acceptance to its logical conclusion, no matter how strange that conclusion became. The result was special relativity. Einstein's 1905 paper on the electrodynamics of moving bodies began with 2 postulates stated with the spare clarity of a mathematician presenting axioms. First, the laws of physics are identical in all inertial reference frames. An inertial frame is simply any perspective moving at constant velocity without acceleration. A person floating motionless in space and a person traveling through space at a steady 10,000 kilometers per second in a perfectly straight line without slowing or turning both occupy inertial frames. Both should observe exactly the same physical laws operating in their immediate environments. No experiment performed locally without reference to outside objects can distinguish between these 2 situations. There is no absolute rest. There is no privileged frame against which all other motion can be measured. Motion is always relative. This first postulate was not entirely new. Galileo himself had understood that the laws of mechanics were the same for observers in uniform motion. A ball dropped inside a smoothly sailing ship falls straight down relative to the ship, exactly as it would on land, because the ship's motion does not affect the ball's behavior relative to the ship's interior. Newton's mechanics obeyed this principle. Einstein extended it to cover all of physics, including electromagnetism. Second, the speed of light in vacuum is the same for all observers, regardless of the motion of the light source or the observer. This second postulate was the one that shattered everything. It contradicted the most basic intuitions about how velocities combine. If you throw a ball forward from a moving train at 10 meters per second, and the train itself moves at 30 meters per second relative to the ground, then the ball moves at 40 meters per second relative to the ground. Velocities add. Everyone knows this. Every child who has ever thrown something from a moving vehicle understands it intuitively. But Einstein said light does not work this way. If you shine a flashlight from a moving spaceship, the light does not travel at the speed of light plus the speed of the spaceship. It travels at exactly the speed of light relative to every observer everywhere, regardless of how fast the spaceship moves. An observer standing still watching the spaceship pass measures the light beam at 299,792 kilometers per second. The astronaut inside the spaceship moving with the source also measures the same beam at 299,792 kilometers per second. An observer running toward the beam at half light speed would still measure it at exactly 299,792 kilometers per second. The beam's speed does not change. It cannot change. It is constant for everyone. This seems impossible. If velocities always add, and the spaceship is moving forward, then the light should move faster relative to stationary observers. If the observer is running toward the beam should appear to approach faster, but neither of these things happens. The speed remains fixed. Something has to give. The 2 postulates together demand it. And what Gibbs Einstein showed is the intuitive assumption that space and time are absolute fixed universal quantities that all observers measure identically. They are not. They never were. Our intuitions misled us because the effects become significant only at velocities far beyond anything humans experience directly. At the speeds of everyday life, the deviations from classical behavior are unmeasurably tiny. At speeds approaching light, they become impossible to ignore. Space and time are not independent absolute quantities. They are interwoven aspects of a single 4-dimensional structure, spacetime, and different observers moving at different velocities slice through that structure differently. What one observer measures as purely temporal duration, another observer measures as a mixture of temporal and spatial intervals. What one measures as purely spatial distance, another measures as a combination of spatial and temporal separation. The two postulates together demand that these slicings adjust in precisely the way needed to keep the speed of light constant for everyone. The specific adjustments have names: time dilation, length contraction, and they are not illusions. Time dilation is the first and most counterintuitive consequence. Moving clocks run slower than stationary clocks. Not because movement damages clockwork mechanisms, not because vibration disturbs the timekeeping. Time itself, the actual passage of physical duration, flows more slowly for observers in motion relative to you. If you watch a clock fly past you at high speed, that clock genuinely ticks more slowly than an identical clock sitting stationary beside you. When the moving clock returns, it will show less elapsed time than the stationary one. The difference is real. It is measurable. It has been measured. The mathematical relationship is captured by a quantity physicists call gamma the Lorentz factor. Gamma equals 1 divided by the square root of the quantity 1 minus velocity squared over light speed squared. This single expression governs everything strange about relativistic motion. When velocity is 0, gamma equals exactly 1. Time flows normally. Physics is boring. As velocity increases, gamma increases slowly at first. At 10% of light speed, roughly 3,000 kilometers per second, gamma equals approximately 1.005. Moving clocks run about 0.5% slower than stationary ones. The effect is real but negligible for practical purposes. You would need to travel at this speed continuously for about 6 months before your watch fell 1 second behind a stationary clock. At 50% of light speed, gamma reaches approximately 1.15. Moving clocks run about 13% slower. Noticeable in principle, but the universe is not yet behaving in ways that violate intuition catastrophically. At 90% of light speed, gamma climbs to approximately 2.3. Time flows at less than half the rate it does for stationary observers. A year of Earth time compresses into roughly 5 months of experience for the traveler. The distortion is dramatic and undeniable. At 99% of light, the world changes while the traveler moves through time in slow motion. At 99.9%, gamma surpasses 22. A decade of travel feels like a year. Civilizations could transform in the time it takes to complete a single long voyage. And as velocity approaches light speed, exactly gamma approaches infinity without limit. Time dilation becomes total. Time stops completely for the traveler relative to the external universe. This is the domain of massless particles. Photons experience this. A photon crossing the observable universe, a journey requiring 13 billion years by any external clock, experiences 0 elapsed time. For the photon, emission and absorption are the same moment. The billions of years separating them exist only for observers who have mass, who cannot travel at light speed, who are forever excluded from the photon's timeless existence. Length contraction accompanies time dilation as its spatial counterpart. Moving objects shrink in the direction of motion. A spacecraft traveling at 90% of light speed, measured by a stationary observer, appears compressed to roughly 44% of its rest length in the direction of travel. Not because it is physically crushed, because space itself contracts for the moving object. The atoms are not closer together. The spatial intervals between them, as measured by stationary observers, are simply smaller. At 99% of light speed, that spacecraft shrinks to about 14% of its rest length. At 99.9%, roughly 4.5%, the contraction accelerates as velocity increases, approaching 0 length at exactly light speed, an impossibility for any object, with physical extent in 3 dimensions. These two effects together, time dilation and length contraction, work in precisely coordinated fashion to maintain light speed constancy for all observers. When you move toward a light beam, your time slows and your measuring rods contract. These distortions adjust your measurements of distance and duration in exactly the right proportions to ensure that the ratio of distance to time, which is speed, remains constant. The mathematics does not permit any other outcome once the two postulates are accepted. E equals mc squared emerged almost as an afterthought in a short paper Einstein published later that same year. a 4-page addendum to the longer relativity paper. But what it contained was perhaps the deepest single equation in the history of physics. Mass and energy are the same thing measured in different units. Not merely related, not merely convertible under extreme conditions, identical, two names for a single underlying reality. The speed of light squared, approximately 90 quadrillion in metric units, is simply the conversion factor between the mass unit and the energy unit, the exchange rate between two ways of measuring the same quantity. 1 kilogram of matter completely converted to energy would release approximately 90 quadrillion joules. This exceeds the annual energy consumption of a medium-sized country. The Sun converts roughly 4 million tons of mass into energy every single second through nuclear fusion, and it has been doing so for 4.5 billion years, and it will continue for another 5 billion, because even at this staggering rate it burns through only a tiny fraction of its total mass. Mass is concentrated energy on a scale that makes the most powerful human technologies look trivially modest. But the deepest significance of E equals mc squared is not nuclear power or nuclear weapons. It is the revelation that the speed of light appears in this fundamental relationship, not because light is somehow involved in the exchange between mass and energy, but because the speed of light is the conversion factor between the spatial and temporal dimensions of spacetime. Mass is the energy of something at rest. Energy is the mass of something in motion. The speed of light squared connects them because it is the fundamental parameter relating space to time in the geometry of the universe. Remove photons from the universe entirely, the equation remains, the conversion factor remains, the speed of light as the natural unit connecting space and time remains. The constant we call light speed was never about light. It was always about the structure of space-time. Einstein's theory was beautiful. It was mathematically elegant. It resolved the crisis created by the Michelson-Morley experiment without rescue hypotheses or contrived mechanisms. It required no ether because it required no medium for light. Light was not a wave in a substance. It was a disturbance in space-time itself, and space-time required no substrate to exist within. But beauty and elegance, however, compelling to physicists, are not proof. The theory needed experimental confirmation, and the confirmations came gradually at first, then overwhelming in their totality. Cosmic ray muons provide one of the most striking everyday confirmations. These unstable subatomic particles are created when high-energy cosmic rays slam into molecules in Earth's upper atmosphere at altitudes around 15 kilometers. Muons decay with a half-life of approximately 2.2 microseconds, traveling at roughly 99.94% of light speed. A muon covers only about 660 meters before half of any large population has decayed. Classical physics predicts that virtually no muons should survive the 15-kilometer journey to ground level. The math is straightforward, the conclusion is clear. Yet, ground-based detectors observe enormous numbers of cosmic ray muons, far more than non-relativistic calculations allow. Time dilation resolves the contradiction perfectly. At 99.94% of light speed gamma equals approximately 30. The muon's internal clock, which governs its decay, runs 30 times slower than clocks on Earth's surface. From our perspective, the muon lives 30 times longer than its rest frame half-life would suggest. It survives the journey because relativity extends its lifetime by a factor of 30, giving it time to reach our detectors before decaying. From the muon's own perspective, the resolution is equally complete, but described differently. The muon is stationary. Earth rushes upward toward it at 99.94% of light speed. The 15 kilometers of atmosphere contracts by a factor of 30. The muon sees only 500 meters of atmosphere to cross. It decays at its normal rate, but the distance is short enough that it survives. Both descriptions are correct. Both yield identical predictions. This is the essence of relativity. The measurements differ between frames. The physical outcomes do not. The global positioning system demonstrates relativistic effects at a scale that affects the daily lives of billions of people who have never heard of time dilation. GPS satellites orbit at roughly 14,000 kilometers per hour. At this velocity, special relativistic time dilation causes their onboard clocks to run approximately 7 microseconds per day, slower than identical clocks on Earth's surface. Simultaneously, the satellites orbit at higher altitude where Earth's gravity is weaker. General relativity, Einstein's later extension of special relativity to include gravity, predicts that clocks run faster in weaker gravitational fields. This effect adds roughly 45 microseconds per day to the satellite clocks relative to surface clocks. The net result is that GPS satellite clocks gain approximately 38 microseconds per day relative to ground-based receivers. 30 and 28 microseconds sounds trivial. It is not. GPS determines position by measuring the time signals take to travel from satellites to receivers. Light travels roughly 11 kilometers in 38 microseconds. Without correcting for relativistic time dilation, GPS position errors would accumulate at approximately 11 kilometers per day. Your navigation application would become useless within hours of deployment. The corrections applied to every GPS satellite in operation are calculated using Einstein's equations. They work. Your navigation works because special and general relativity are not approximations or convenient fictions. They are accurate descriptions of how time actually flows in the real universe. The Large Hadron Collider at CERN confirms relativistic mechanics with precision that borders on the incomprehensible. Protons circulating in that 27-kilometer ring travel at 99.9991% of light speed. Their gamma factor exceeds 7,000. The magnets guiding them around the ring must exert forces calculated using relativistic equations for momentum which scales with gamma, rather than following the classical formula. If classical physics governed those protons, the magnetic fields would be wildly miscalibrated. The beams would spiral outward and smash into the tunnel walls within seconds. The collider functions producing physics, results that have confirmed and extended our understanding of fundamental particles precisely because the relativistic equations describing the proton's motion are exactly correct. Special relativity has been tested with extraordinary precision across more than a century of increasingly refined experiments. Not one experimental result has contradicted it. Not one measurement has revealed a deviation from its predictions. Every test confirms the same conclusion. The speed of light is absolute. Space and time adjust to maintain it. The universe is constructed the way Einstein said it was in 1905, sitting at that wooden desk in the patent office in Bern. And yet, Einstein's theory is silent on the deepest question. It shows precisely what happens as objects approach light speed. It demonstrates with mathematical certainty why reaching it requires infinite energy. It predicts every experimental result with exact accuracy, but it does not explain why. Why is spacetime structured this way? Why does gamma diverge as velocity approaches light speed rather than some other behavior? Why is the cosmic speed limit this particular value and not some other? Einstein built special relativity on two postulates he accepted, without deeper justification. They were true. Their consequences were exactly right. But they were postulates, assumptions, starting points, not derivations from something more fundamental. The explanation for why these postulates are true, why the universe is constructed with this particular structure, would require a completely different kind of physics. It would require understanding not just how particles move through space-time, but what particles actually are at the most fundamental level. It would require quantum mechanics to mature into quantum field theory. And it would require a young physicist from far Rockaway, New York, to develop an entirely new way of visualizing how reality works at the smallest scales. When Richard Feynman finally answered the question that Einstein could not answer, revealed something that should make you pause and sit quietly for a moment. The speed of light is not a limit imposed on the universe from outside. It is not a wall constructed to prevent certain kinds of motion. It is a consequence of the deepest rules governing how quantum amplitudes combine to produce physical reality. Faster than light motion does not violate the rules. It simply cancels itself out before it can contribute anything to existence. There is no barrier to break through. There is nothing on the other side. But to understand what Feynman found, we must first understand exactly what happens physically as objects accelerate toward the light speed boundary. Because the mathematics of that approach, the way the energy requirements climb toward infinity, and the way the universe resists every increment of additional velocity with ever-increasing stubbornness, reveals something profound about why the barrier is not merely difficult to cross, but meaningless to attempt. The universe does not fight you as you approach light speed. It simply runs out of places for you to go. Picture yourself strapped into the cockpit of an impossible spacecraft. Not a spacecraft constrained by the engineering limitations of the present, not a vehicle limited by the fuel densities of chemical rockets or the power outputs of nuclear reactors. An impossible spacecraft, one that physicists use as a thought experiment precisely because it removes every practical obstacle and confronts only the fundamental ones. This craft has unlimited fuel. Its engine operates at perfect efficiency, converting every gram of propellant into exactly as much thrust as the laws of physics permit. Its structure is perfectly rigid. Its systems never fail. You have unlimited time and unlimited resources and a single mission. Accelerate until you break the light speed barrier. You ignite the engines. Thrust presses you back into your seat with steady, comfortable force. Your velocity climbs. The stars ahead blue shift slightly, their light compressed toward shorter wavelengths by your motion toward them. The stars behind redden their light, stretched by your retreat. These are beautiful effects, observable consequences of your increasing speed, and they tell you that something real is happening. You are moving faster through space than you were a moment ago. 1% of light speed, roughly 3000 kilometers per second, fast enough to cross the continental United States in the time it takes to snap your fingers. The engines burn steadily. The fuel flows smoothly. Everything feels exactly as straightforward as classical physics would predict. 5%, 10%. The velocity climbs with reassuring regularity. Each unit of fuel burned produces a predictable increment of speed. You are covering ground. You are making progress. The universe appears willing to let you accelerate indefinitely. You cross 20% of light speed, 30, 40. Then you cross 50% and something changes. Not dramatically, not catastrophically. The engines have not weakened. The fuel supply remains abundant. The thrust pressing you into your seat feels exactly as strong as before, but the velocity readout climbs more slowly. Each additional percentage point of speed costs noticeably more fuel than the previous one. The easy linear relationship between energy input and velocity output has quietly broken. The universe has begun pushing back. Not hard yet, but the resistance is there, real and measurable. And it was not there before. You push harder, more fuel, more thrust. 60% of light speed, 70. The curve of diminishing returns steepens with each increment. At 80%, each additional unit of velocity demands substantially more energy than the last. At 90%, the situation has transformed from challenging to alarming. Adding the final 10 percentage points to reach light speed, you realize would require more energy than you have spent reaching 90% from rest. Not twice as much. Not 10 times as much. The energy requirement has begun climbing toward a mathematical infinity that no finite fuel supply can ever reach. You are not fighting friction. Space is empty. You are not fighting air resistance. There is no air. You are not fighting any force that engineering could overcome or that a better engine could push through. You are fighting the structure of spacetime itself. And spacetime always wins. The mathematics of what is happening to your spacecraft reveals the shape of the barrier with uncomfortable precision. The gamma factor which Einstein introduced and which governs everything strange about relativistic motion tells the complete story. Gamma equals 1 divided by the square root of the quantity 1 minus your velocity squared over light speed squared. At low velocities, this expression stays close to 1. Physics behaves normally. The universe is cooperative. As velocity increases, the denominator of this fraction shrinks. The quantity inside the square root 1 minus velocity squared over light speed squared approaches 0 as velocity approaches light speed. The square root of a number approaching 0 is itself approaching 0. 1 divided by something approaching 0 is something approaching infinity. Gamma climbs without limit. At 50% of light speed, gamma equals approximately 1.15. Your resistance to further acceleration is 15% higher than at rest. The universe pushes back gently, a firm hand rather than a wall. At 90%, gamma reaches approximately 2.3. The same thrust that initially produced significant velocity gains now produces less than half the acceleration it did at low speeds. You are working noticeably harder for diminishing returns. At 99%, gamma exceeds 7. Every increment of speed costs 7 times more energy than the same increment at rest. Your engines strain against a universe that has become deeply reluctant to cooperate. At 99.9%, gamma surpasses 22. At 99.99%, it exceeds 70. Each additional 9 added to your velocity multiplies gamma by roughly 3, and each multiplication makes the next increment of speed exponentially more expensive. The pattern continues without interruption, without plateau, without any sign of leveling off at some large but finite value. At exactly light speed, gamma reaches infinity, not a large number that we approximate as infinite for convenience. Mathematical infinity, precise, exact, unapproachable infinity. The energy required to accelerate any object with mass to precisely light speed is not merely very large, it is infinite. It exceeds any finite quantity that could be named, produced, or imagined. It exceeds the total energy content of the observable universe. It exceeds the energy content of 1 trillion observable universes. No amount of fuel, no advancement in propulsion technology, no theoretical breakthrough in energy generation can overcome mathematical infinity. Infinity is not an engineering problem. It is a statement about the structure of existence. The Large Hadron Collider, beneath the French-Swiss border, makes this abstract mathematics tangible in a way that should stop you completely. This machine, a ring 27 kilometers in circumference, buried roughly 100 meters underground, accelerates protons to 99.9991% of light speed. Read those 9s carefully and let them settle. The protons achieve a velocity just 7 parts in 10 billion shy of light speed itself. 7 parts in 10 billion. The remaining gap between the protons and the speed of light is so small that if you represented the full range from rest to light speed as the distance between two cities separated by 1,000 kilometers, the remaining gap would be about 7 millimeters. At this velocity, each proton carries a gamma factor exceeding 7,000. Its relativistic momentum is 7,000 times what classical physics would calculate. The magnetic fields guiding those protons around the ring must be calibrated using relativistic equations because the forces required to bend a relativistic proton's path are thousands of times larger than classical mechanics would predict. The engineers who designed the superconducting magnets lining that tunnel used Einstein's equations, not Newton's, because Newton's equations are simply wrong at these velocities. Consider what it would require to push those protons the remaining 7 parts in 10 billion toward light speed. The energy requirement does not increase gradually. It does not scale linearly or even polynomially with the remaining gap. It explodes upward asymptotically. Closing half the remaining gap would require more energy than the entire collider currently expends. Closing half of that remaining half would require more still. Each halving of the residual distance demands exponentially more power than the previous halving. To actually reach light speed would require the total energy budget of a civilization, drawing power from an entire galaxy sustained for longer than the current age of the universe. And even then, it would not be enough, because the energy requirement is not merely very large, it is infinite. There is no number large enough. There is no power source sufficient. The barrier is not an engineering challenge awaiting a cleverer solution. It is a mathematical property of spacetime that no physical process can circumvent. Time dilation adds another layer to the impossibility, one that operates simultaneously and reinforces the energy barrier from a completely different direction. As your impossible spacecraft approaches, light speed time aboard begins flowing differently than time in the universe outside. At 90% of light speed, your clocks run at less than half the rate of stationary clocks. A year of Earth time compresses into roughly 5 months of your subjective experience. You are aging noticeably slower than the observers you left behind. At 99%, your clocks run at about 14% of normal speed. 7 years pass on Earth for every year you experience. At 99.9%, your time slows to roughly 4.5% of external time. A century of Earth time would pass during less than 5 years of your subjective experience. Civilizations could rise and collapse between your departure and return. As velocity approaches light speed, exactly time dilation approaches its own infinity. Time aboard your spacecraft would stop completely relative to the external universe. Not slow to a crawl, not approach some minimum tick rate. Stop. Completely. The interval between any two events aboard your ship, as measured by any external observer, would stretch to infinite duration. You would be frozen in a single moment, extended infinitely through external time, never moving forward, never aging, never changing. This is the domain of massless particles. Photons exist in this realm of frozen time. The photon that left a distant star a billion years ago and strikes your retina tonight experienced no duration in between, for the photon emission and absorption were the same moment. The billion years existed only for the massive universe. The photon crossed, not for the photon itself. This is not poetry. This is the measured, verified behavior of massless particles in a universe governed by special relativity. Massive particles cannot enter this domain. They are barred not by any enforcement mechanism but by the mathematics of gamma. Reaching exactly light speed requires gamma to become infinite, which requires infinite energy, which is impossible. The frozen time realm belongs exclusively to the massless. Everything with mass is forever excluded, not by rule, by structure. Length contraction closes the triangle of impossibility from the third direction. At exactly light speed, an object would contract to zero length in the direction of motion. This is not compression in any physical sense, not atoms being squeezed closer together by force. It is space itself collapsing to zero extent for the moving object. Any physically real three-dimensional object possessing actual extent in the direction of travel cannot have zero length in that direction without ceasing to exist as a three-dimensional object. The mathematics does not prohibit this. It simply describes a situation that has no physical realization. Three separate mathematical impossibilities, each approached from a different direction, each reinforcing the others, each describing the same underlying truth from a different angle. The light-speed barrier is not one wall. It is the point at which every description of physical reality simultaneously fails to extend further. There is no path through. There is no path around. There is no path above. The barrier is not a feature of the landscape. It is the edge of the landscape itself. The natural response to absolute barriers is to search for loopholes. Human ingenuity has circumvented enough apparently absolute limits throughout history that the instinct is understandable. We were told heavier-than-air flight was impossible. We were told human beings could not survive speeds above a certain threshold. We were told we could never leave Earth's gravity. Each of these limits turned out to be practical, rather than fundamental. Engineering constraints that collapsed under sufficient creativity. Perhaps the light speed limit is the same. Perhaps sufficiently advanced technology, physics we have not yet discovered, could find a path around the constraint. Perhaps the barrier is harder than any we have previously overcome, but not categorically different in kind. It is categorically different in kind. Tachyons represent the most straightforward proposed loophole. These hypothetical particles would travel permanently faster than light existing in a domain above the barrier, rather than attempting to cross it. Just as ordinary matter exists permanently below light speed and cannot accelerate upward through the barrier, tachyons would exist permanently above and could not decelerate downward through it. The two domains would be forever separated by the light-speed boundary, which neither could cross. The mathematics of tachyons is internally consistent in a narrow technical sense. You can write equations describing particles with imaginary rest mass, a mathematical property that inverts the usual relationship between energy and velocity. In classical special relativity, massive particles require infinite energy to reach light speed. Tachyons with imaginary mass would require infinite energy to slow down to light speed. The symmetry is elegant. The problem is causality. In special relativity, faster than light travel is mathematically equivalent to backward time travel. This is not an interpretation or a philosophical concern. It is a direct consequence of the Lorentz transformations that Einstein derived. For any faster-than-light signal, there exists a reference frame in which that signal travels backward in time. Different observers moving at different velocities would disagree about whether a tachyon signal traveled toward the future or toward the past. For some observers, a tachyon message would arrive before it was sent. The effect would precede the cause. This creates paradoxes that cannot be resolved within any logically consistent framework. You could receive information about a future event and use that information to prevent the event from occurring. The event would then not occur, so you would not receive the information. So you could not prevent the event, so the event would occur, so you would receive the information, cycling endlessly without resolution. These are not puzzles awaiting clever solutions. They are logical contradictions that destroy the coherence of physical law. A universe permitting tachyons would be a universe without reliable causality. Causes could fail to produce their effects because the effects could retroactively eliminate the causes. The orderly sequence of events from which all meaning emerges would dissolve into self-referential contradiction. No experiment has ever detected a tachyon. No theoretical framework has successfully incorporated them without generating exactly these paradoxes. The evidence is overwhelming that they do not exist. Quantum tunneling appears at first to offer a more promising route. In quantum mechanics, particles can appear on the far side of barriers they classically could not penetrate. An electron encountering a potential energy barrier too tall to climb sometimes emerges on the other side without having gone over it or around it. The particle tunnels through. The effect is real, experimentally confirmed thousands of times daily in transistors scanning tunneling microscopes and nuclear fusion reactions in stellar cores. Quantum mechanics permits things that classical physics strictly forbids. Could quantum tunneling provide passage through the light-speed barrier? Could particles tunnel from subluminal velocities to superluminal ones, the way electrons tunnel through potential energy barriers? Careful analysis shows that it cannot, and the reason reveals something important about what tunneling actually is. A quantum particle approaching a barrier is not a tiny billiard ball with a precise location and velocity. It is a spread-out wave packet, with a front edge, a center, and a trailing edge. When this wave packet encounters a barrier, part of it tunnels through, but the transmitted portion is reshaped during transmission. The center of the transmitted packet can emerge on the far side before the center of the incoming packet has fully entered the barrier on the near side. If you naively measure from peak to peak, the transmission appears superluminal. The transmitted pulse seems to arrive faster than light would travel the same distance through empty space. Experiments in the 1990s measured exactly this effect and initially generated considerable excitement. Had faster than light transmission been observed? Had quantum mechanics found the loophole that classical physics missed? No, and the reason is subtle but decisive. Information is not carried by the peak of a wave packet. Information is carried by the leading edge, the front of the packet, the first disturbance arriving at the far side, and the leading edge of the transmitted packet never emerges before causality permits. It never arrives before a light signal sent simultaneously from the barrier's near side would arrive. The apparent superluminal behavior is entirely a reshaping effect, a reorganization of the packet's internal structure during transmission, not a genuine transfer of information faster than light. This distinction between apparent and genuine superluminal transmission is not a technicality. It is the entire point. Physics permits all manner of apparent effects that seem to violate causality upon naive inspection. What physics absolutely prohibits is the actual transmission of information faster than light. Quantum tunneling, examined carefully, respects this prohibition with the same rigor as everything else. The Alcubierre warp drive represents the most sophisticated loophole proposal, one that generated genuine excitement among physicists when Miguel Alcubierre published it in 1994 because it appeared to exploit general relativity itself as the mechanism of apparent superluminal travel. Alcubierre proposed that a spacecraft might never need to travel faster than light locally. While still covering cosmic distances, faster than light could travel through undistorted space. The mechanism involves contracting spacetime in front of the spacecraft and expanding it behind. The ship sits in a bubble of locally flat spacetime stationary relative to its immediate surroundings. The bubble itself moves through the surrounding spacetime at any desired speed, including speeds faster than light. The ship never exceeds light speed within its local bubble, yet the bubble's motion carries the ship to arbitrarily distant destinations in arbitrarily short times. The mathematics is internally consistent within general relativity. Einstein's equations permit this metric. Space-time can in principle curve and distort in exactly the ways Alcubierre described. The proposal does not obviously violate any fundamental principle. The problems emerge when you ask what it would actually require to create and sustain such a bubble. The energy requirements are not merely large, they are not merely impractical by current technology. They require exotic matter with negative energy density matter that gravitationally repels rather than attracts, matter that produces effects opposite to everything we have ever observed in the universe. While quantum mechanics permits tiny amounts of negative energy under very specific conditions, the quantities required for an Alcubierre bubble of any useful size exceed the total positive energy content of the observable universe by many orders of magnitude. More recent analyses have revealed deeper problems. The leading edge of the warp bubble would accumulate radiation and particles to catastrophic densities as it moved. Dropping the bubble upon arrival would release this accumulated energy in a catastrophic blast capable of sterilizing entire star systems. The passengers inside the bubble could not steer it or control it because no signal from inside can reach the bubble's wall faster than light. And the exotic matter required to create the bubble cannot be produced by any known physics and may be fundamentally prohibited by the actual behavior of quantum fields in curved spacetime. The Alcubierre drive remains what it has always been, a beautiful mathematical exercise demonstrating that general relativity contains solutions that superficially resemble what science fiction imagines. Not a blueprint, not a research direction, a demonstration that the equations are flexible enough to describe geometries we cannot realize and may never be able to realize. Traversable wormholes encounter the same obstacle from a different angle. These hypothetical tunnels through spacetime connecting distant regions through shortcuts in the underlying geometry appear as solutions to Einstein's field equations. The mathematics permits them. They could in principle allow travelers to emerge far from their starting point without crossing the intervening distance at all, covering effectively superluminal distances without locally exceeding light speed at any point, but maintaining a traversable wormhole, keeping it open and stable long enough for passage, requires the same exotic matter with negative energy density that Alcubierre's drive demands. Natural wormholes, if they exist at all, would be microscopic quantum fluctuations in spacetime geometry, arising and collapsing on scales far smaller than an atomic nucleus, far too small for any particle to traverse. Expanding them to human scale, let alone spacecraft scale, would require exotic matter in quantities that exceed anything quantum mechanics permits by an enormous margin. Every proposed loophole examined carefully encounters the same fundamental obstacle, not an engineering limitation awaiting more advanced technology, not a practical constraint that future physics might dissolve. A property of how spacetime connects events, a feature of the causal structure of the universe that no amount of cleverness can circumvent, because the causal structure is not a constraint imposed on the universe from outside. It is the universe. And yet, all of these impossibilities, the infinite energy requirement, the infinite time dilation, the complete length contraction, the paradoxes of tachyons, the exotic matter, demands of every proposed workaround, all of them tell you what happens, none of them tell you why. Why is the universe constructed with this particular causal structure? Why does gamma diverge at exactly light speed? Why do the equations of general relativity permit wormholes and warp drives in mathematical form, while the physical universe denies them the exotic matter they require? Why do tachyon causality violations feel like logical contradictions rather than merely unusual phenomena? Einstein showed us the architecture of the barrier, He mapped its contours with extraordinary precision. His equations predict every consequence of approaching it with accuracy that no experiment has ever contradicted. But he did not explain why the architecture exists. His postulates described the structure of spacetime without deriving it from anything deeper. The deeper explanation exists. It was found not through geometry or thought experiments about catching up to light beams, but through a completely different kind of inquiry, one that asks not how particles move through spacetime, but what particles actually are, what reality is made of at its most fundamental level, and how the rules governing that level conspire to produce automatically and inevitably the universe that Galileo tried to measure on that hillside outside Florence, that Raymer glimpsed in the drifting eclipses of Io, that Einstein captured in two postulates that seemed almost too simple to contain what they contained. Richard Feynman found it, and what he found will require you to abandon every remaining intuition about what motion means at the quantum level, because at that level, motion is not what you think it is. Particles do not travel from one place to another along paths. They travel along every path simultaneously. And it is in the mathematics of that simultaneous exploration of all possible paths that the speed of light emerges, not as a limit, not as a barrier, but as the natural consequence of what it means for a quantum amplitude to contribute to observable reality. The answer is not that faster than light paths are forbidden. The answer is that faster than light paths cancel themselves out of existence before they can matter. Picture yourself strapped into the cockpit of an impossible spacecraft. Not a spacecraft constrained by the engineering limitations of the present. Not a vehicle limited by the fuel densities of chemical rockets or the power outputs of nuclear reactors. An impossible spacecraft, one that physicists use as a thought experiment precisely because it removes every practical obstacle and confronts only the fundamental ones. This craft has unlimited fuel. Its engine operates at perfect efficiency, converting every gram of propellant into exactly as much thrust as the laws of physics permit. Its structure is perfectly rigid. Its systems never fail. You have unlimited time and unlimited resources and a single mission. Accelerate until you break the light speed barrier. You ignite the engines. Thrust presses you back into your seat with steady, comfortable force. Your velocity climbs. The stars ahead blue shift slightly, their light compressed toward shorter wavelengths by your motion toward them. The stars behind redden their light stretched by your retreat. These are beautiful effects, observable consequences of your increasing speed, and they tell you that something real is happening. You are moving faster through space than you were a moment ago. 1% of light speed, roughly 3000 kilometers per second. Fast enough to cross the continental United States in the time it takes to snap your fingers. The engines burn steadily. The fuel flows smoothly. Everything feels exactly as straightforward as classical physics would predict. 5%, 10%, the velocity climbs with reassuring regularity. Each unit of fuel burned produces a predictable increment of speed. You are covering ground. You are making progress. The universe appears willing to let you accelerate indefinitely. You cross 20% of light speed, 30, 40. Then you cross 50% and something changes. Not dramatically, not catastrophically. The engines have not weakened. The fuel supply remains abundant. The thrust pressing you into your seat feels exactly as strong as before. But the velocity readout climbs more slowly. Each additional percentage point of speed costs noticeably more fuel than the previous one. The easy linear relationship between energy input and velocity output has quietly broken. The universe has begun pushing back. Not hard yet, but the resistance is there, real and measurable, and it was not there before. You push harder. More fuel, more thrust. 60% of light speed, 70. The curve of diminishing returns steepens with each increment. At 80%, each additional unit of velocity demands substantially more energy than the last. At 90%, the situation has transformed from challenging to alarming. Adding the final 10 percentage points to reach light speed, you realize how would require more energy than you have spent reaching 90% from rest. Not twice as much. Not 10 times as much. The energy requirement has begun climbing toward a mathematical infinity that no finite fuel supply can ever reach. You are not fighting friction. Space is empty. You are not fighting air resistance. There is no air. You are not fighting any force that engineering could overcome or that a better engine could push through. You are fighting the structure of space-time itself. And space-time always wins. The mathematics of what is happening to your spacecraft reveals the shape of the barrier with uncomfortable precision. The gamma factor, which Einstein introduced, and which governs everything strange about relativistic motion, tells the complete story. Gamma equals 1 divided by the square root of the quantity 1 minus your velocity squared over light speed squared. At low velocities, this expression stays close to 1. Physics behaves normally. The universe is cooperative. As velocity increases, the denominator of this fraction shrinks. The quantity inside the square root 1 minus velocity squared over light speed squared approaches 0 as velocity approaches light speed. The square root of a number approaching 0 is itself approaching 0. 1 divided by something approaching 0 is something approaching infinity. Gamma climbs without limit. At 50% of light speed, gamma equals approximately 1.15. Your resistance to further acceleration is 15% higher than at rest. The universe pushes back gently, a firm hand rather than a wall. At 90%, gamma reaches approximately 2.3. The same thrust that initially produced significant velocity gains now produces less than half the acceleration it did at low speeds. You are working noticeably harder for diminishing returns. At 99%, gamma exceeds 7. Every increment of speed costs 7 times more energy than the same increment at rest. Your engines strain against a universe that has become deeply reluctant to cooperate. At 99.9%, gamma surpasses 22. At 99.99%, it exceeds 70. Each additional 9 added to your velocity multiplies gamma by roughly 3, and each multiplication makes the next increment of speed exponentially more expensive. The pattern continues without interruption, without plateau, without any sign of leveling off at some large but finite value. At exactly light speed, gamma reaches infinity, not a large number that we approximate as infinite for convenience. Mathematical infinity, precise, exact, unapproachable infinity. The energy required to accelerate any object with mass to precisely light speed is not merely very large, it is infinite. It exceeds any finite quantity that could be named, produced, or imagined. It exceeds the total energy content of the observable universe. It exceeds the energy content of 1 trillion observable universes. No amount of fuel, no advancement in propulsion technology, no theoretical breakthrough in energy generation can overcome mathematical infinity. Infinity is not an engineering problem. It is a statement about the structure of existence. The Large Hadron Collider beneath the French-Swiss border makes this abstract mathematics tangible in a way that should stop you completely. This machine, a ring 27 kilometers in circumference, buried roughly 100 meters underground, accelerates protons to 99.9991% of light speed. Read those 9s carefully and let them settle. The protons achieve a velocity just 7 parts in 10 billion shy of light speed itself. 7 parts in 10 billion. The remaining gap between the protons and the speed of light is so small that if you represented the full range from rest to light speed as the distance between 2 cities separated by 1,000 kilometers, the remaining gap would be about 7 millimeters. At this velocity, each proton carries a gamma factor exceeding 7,000. Its relativistic momentum is 7,000 times what classical physics would calculate. The magnetic fields guiding those protons around the ring must be calibrated using relativistic equations because the forces required to bend a relativistic proton's path are thousands of times larger than classical mechanics would predict. The engineers who designed the superconducting magnets lining that tunnel used Einstein's equations, not Newton's, because Newton's equations are simply wrong at these velocities. Consider what it would require to push those protons the remaining 7 parts in 10 billion toward light speed. The energy requirement does not increase gradually. It does not scale linearly or even polynomially with the remaining gap. It explodes upward, asymptotically. Closing half the remaining gap would require more energy than the entire collider currently expends. Closing half of that remaining half would require more still. Each halving of the residual distance demands exponentially more power than the previous halving. To actually reach light speed would require the total energy budget of a civilization drawing power from an entire galaxy sustained for longer than the current age of the universe. And even then, it would not be enough, because the energy requirement is not merely very large. It is infinite. There is no number large enough. There is no power source sufficient. The barrier is not an engineering challenge awaiting a cleverer solution. It is a mathematical property of spacetime that no physical process can circumvent. Time dilation adds another layer to the impossibility, one that operates simultaneously and reinforces the energy barrier from a completely different direction. As your impossible spacecraft approaches light speed, time aboard begins flowing differently than time in the universe outside. At 90% of light speed, your clocks run at less than half the rate of stationary clocks. A year of Earth time compresses into roughly 5 months of your subjective experience. You are aging noticeably slower than the observers you left behind. At 99%, your clocks run at about 14% of normal speed. 7 years pass on Earth for every year you experience. At 99.9%, your time slows to roughly 4.5% of external time. A century of Earth time would pass during less than 5 years of your subjective experience. Civilizations could rise and collapse between your departure and return. As velocity approaches light speed, exactly time dilation approaches its own infinity. Time aboard your spacecraft would stop completely relative to the external universe. Not slow to a crawl, not approach some minimum tick rate. Stop completely. The interval between any two events aboard your ship, as measured by any external observer, would stretch to infinite duration. You would be frozen in a single moment extended infinitely through external time, never moving forward, never aging, never changing. This is the domain of massless particles. Photons exist in this realm of frozen time. The photon that left a distant star 1 billion years ago and strikes your retina tonight experienced no duration in between. For the photon emission and absorption were the same moment. The billion years existed only for the massive universe. The photon crossed, not for the photon itself. This is not poetry. This is the measured, verified behavior of massless particles in a universe governed by special relativity. Massive particles cannot enter this domain. They are barred not by any enforcement mechanism, but by the mathematics of gamma. Reaching exactly light speed requires gamma to become infinite, which requires infinite energy, which is impossible. The frozen time realm belongs exclusively to the massless. Everything with mass is forever excluded, not by rule, by structure. Length contraction closes the triangle of impossibility from the third direction. At exactly light speed, an object would contract to 0 length in the direction of motion. This is not compression in any physical sense, not atoms being squeezed closer together by force. It is space itself collapsing to 0 extent for the moving object. Any physically real 3-dimensional object possessing actual extent in the direction of travel cannot have 0 length in that direction without ceasing to exist as a 3-dimensional object. The mathematics does not prohibit this. It simply describes a situation that has no physical realization. 3 separate mathematical impossibilities, each approached from a different direction, each reinforcing the others, each describing the same underlying truth from a different angle. The light speed barrier is not one wall. It is the point at which every description of physical reality simultaneously fails to extend further. There is no path through, there is no path around, there is no path above. The barrier is not a feature of the landscape. It is the edge of the landscape itself. The natural response to absolute barriers is to search for loopholes. Human ingenuity has circumvented enough apparently absolute limits throughout history that the instinct is understandable. We were told heavier than air flight was impossible. We were told human beings could not survive speeds above a certain threshold. We were told we could never leave Earth's gravity. Each of these limits turned out to be practical rather than fundamental. engineering constraints that collapsed under sufficient creativity. Perhaps the light speed limit is the same. Perhaps sufficiently advanced technology physics we have not yet discovered could find a path around the constraint. Perhaps the barrier is harder than any we have previously overcome, but not categorically different in kind. It is categorically different in kind. Tachyons represent the most straightforward proposed loophole. These hypothetical particles would travel permanently faster than light existing in a domain above the barrier, rather than attempting to cross it. Just as ordinary matter exists permanently below light speed and cannot accelerate upward through the barrier, tachyons would exist permanently above and could not decelerate downward through it. The two domains would be forever separated by the light speed boundary, which neither could cross. The mathematics of tachyons is internally consistent in a narrow technical sense. You can write equations describing particles with imaginary rest mass, a mathematical property that inverts the usual relationship between energy and velocity. In classical special relativity, massive particles require infinite energy to reach light speed. Tachyons with imaginary mass would require infinite energy to slow down to light speed. The symmetry is elegant. The problem is causality. In special relativity, faster than light travel is mathematically equivalent to backward time travel. This is not an interpretation or a philosophical concern. It is a direct consequence of the Lorentz transformations that Einstein derived. For any faster-than-light signal, there exists a reference frame in which that signal travels backward in time. Different observers moving at different velocities would disagree about whether a tachyon signal traveled toward the future or toward the past. For some observers, a tachyon message would arrive before it was sent. The effect would precede the cause. This creates paradoxes that cannot be resolved within any logically consistent framework. You could receive information about a future event and use that information to prevent the event from occurring. The event would then not occur, so you would not receive the information, so you could not prevent the event, so the event would occur. So you would receive the information cycling endlessly without resolution. These are not puzzles awaiting clever solutions. They are logical contradictions that destroy the coherence of physical law. A universe permitting tachyons would be a universe without reliable causality. Causes could fail to produce their effects because the effects could retroactively eliminate the causes. The orderly sequence of events from which all meaning emerges would dissolve into self-referential contradiction. No experiment has ever detected a tachyon. No theoretical framework has successfully incorporated them without generating exactly these paradoxes. The evidence is overwhelming that they do not exist. Quantum tunneling appears at first to offer a more promising route. In quantum mechanics, particles can appear on the far side of barriers they classically could not penetrate. An electron encountering a potential energy barrier, too tall to climb, sometimes emerges on the other side without having gone over it or around it. The particle tunnels through. The effect is real, experimentally confirmed thousands of times daily in transistors, scanning, tunneling microscopes, and nuclear fusion reactions in stellar cores. Quantum mechanics permits things that classical physics strictly forbids. Could quantum tunneling provide passage through the light-speed barrier? Could particles tunnel from subluminal velocities to superluminal ones, the way electrons tunnel through potential energy barriers? Careful analysis shows that it cannot, and the reason reveals something important about what tunneling actually is. A quantum particle approaching a barrier is not a tiny billiard ball with a precise location and velocity. It is a spread-out wave packet with a front edge, a center, and a trailing edge. When this wave packet encounters a barrier, part of it tunnels through, but the transmitted portion is reshaped during transmission. The center of the transmitted packet can emerge on the far side before the center of the incoming packet has fully entered the barrier on the near side. If you naively measure from peak to peak, the transmission appears superluminal. The transmitted pulse seems to arrive faster than light would travel the same distance through empty space. Experiments in the 1990s measured exactly this effect and initially generated considerable excitement. Had faster-than-light transmission been observed? Had quantum mechanics found the loophole that classical physics missed? No. And the reason is subtle but decisive. Information is not carried by the peak of a wave packet. Information is carried by the leading edge, the front of the packet, for the first disturbance arriving at the far side. and the leading edge of the transmitted packet never emerges before causality permits. It never arrives before a light signal sent simultaneously from the barrier's near side would arrive. The apparent superluminal behavior is entirely a reshaping effect, a reorganization of the packet's internal structure during transmission, not a genuine transfer of information faster than light. This distinction between apparent and genuine superluminal transmission is not a technicality. It is the entire point. Physics permits all manner of apparent effects that seem to violate causality upon naive inspection. What physics absolutely prohibits is the actual transmission of information faster than light. Quantum tunneling examined carefully respects this prohibition with the same rigor as everything else. The Alcubierre warp drive represents the most sophisticated loophole proposal, one that generated genuine excitement among physicists when Miguel Alcubierre published it in 1994 because it appeared to exploit general relativity itself as the mechanism of apparent superluminal travel. Alcubierre proposed that a spacecraft might never need to travel faster than light locally, while still covering cosmic distances faster than light could travel through undistorted space. The mechanism involves contracting spacetime in front of the spacecraft and expanding it behind. The ship sits in a bubble of locally flat spacetime stationary, relative to its immediate surroundings. The bubble itself moves through the surrounding spacetime at any desired speed, including speeds faster than light. The ship never exceeds light speed within its local bubble, yet the bubble's motion carries the ship to arbitrarily distant destinations in arbitrarily short times. The mathematics is internally consistent within general relativity. Einstein's equations permit this metric. Spacetime can in principle curve and distort in exactly the ways Alcubierre described. The proposal does not obviously violate any fundamental principle. The problems emerge when you ask what it would actually require to create and sustain such a bubble. The energy requirements are not merely large. They are not merely impractical by current technology. They require exotic matter with negative energy density matter that gravitationally repels rather than attracts, matter that produces effects opposite to everything we have ever observed in the universe. While quantum mechanics permits tiny amounts of negative energy under very specific conditions, the quantities required for an Alcubierre bubble of any useful size exceed the total positive energy content of the observable universe by many orders of magnitude. More recent analyses have revealed deeper problems. The leading edge of the warp bubble would accumulate radiation and particles to catastrophic densities as it moved. Dropping the bubble upon arrival would release this accumulated energy in a catastrophic blast capable of sterilizing entire star systems. The passengers inside the bubble could not steer it or control it because no signal from inside can reach the bubble's wall faster than light, and the exotic matter required to create the bubble cannot be produced by any known physics and may be fundamentally prohibited by the actual behavior of quantum fields in curved spacetime. The Alcubierre drive remains what it has always been, a beautiful mathematical exercise demonstrating that general relativity contains solutions that superficially resemble what science fiction imagines, not a blueprint, not a research direction, a demonstration that the equations are flexible enough to describe geometries we cannot realize and may never be able to realize. Traversable wormholes encounter the same obstacle from a different angle. These hypothetical tunnels through spacetime connecting distant regions through shortcuts in the underlying geometry appear as solutions to Einstein's field equations. The mathematics permits them. They could, in principle, allow travelers to emerge far from their starting point without crossing the intervening distance at all, covering effectively superluminal distances without locally exceeding light speed at any point. But maintaining a traversable wormhole, keeping it open and stable long enough for passage, requires the same exotic matter with negative energy density that Alcubierre's drive demands. Natural wormholes, if they exist at all, would be microscopic quantum fluctuations in spacetime geometry, arising and collapsing on scales far smaller than an atomic nucleus, far too small for any particle to traverse. Expanding them to human scale, let alone spacecraft scale, would require exotic matter in quantities that exceed anything quantum mechanics permits by an enormous margin. Every proposed loophole examined carefully encounters the same fundamental obstacle, not an engineering limitation awaiting more advanced technology, not a practical constraint that future physics might dissolve, a property of how space-time connects events, a feature of the causal structure of the universe that no amount of cleverness can circumvent, because the causal structure is not a constraint imposed on the universe from outside. It is the universe. And yet, all of these impossibilities, the infinite energy requirement, the infinite time dilation, the complete length contraction, the paradoxes of tachyons, the exotic matter demands of every proposed workaround, all of them tell you what happens. None of them tell you why. Why is the universe constructed with this particular causal structure? Why does gamma diverge at exactly light speed? Why do the equations of general relativity permit wormholes and warp drives in mathematical form, while the physical universe denies them the exotic matter they require? Why do tachyon causality violations feel like logical contradictions rather than merely unusual phenomena? Einstein showed us the architecture of the barrier. He mapped its contours with extraordinary precision. His equations predict every consequence of approaching it with accuracy that no experiment has ever contradicted. But he did not explain why the architecture exists. His postulates described the structure of space-time without deriving it from anything deeper. The deeper explanation exists. It was found not through geometry or thought experiments about catching up to light beams, but through a completely different kind of inquiry, one that asked not how particles move through space-time, but what particles actually are, what reality is made of at its most fundamental level, and how the rules governing that level conspire to produce automatically and inevitably the universe that Galileo tried to measure on that hillside outside Florence, that Remer glimpsed in the drifting eclipses of Io, that Einstein captured in two postulates that seemed almost too simple to contain what they contained. Richard Feynman found it, and what he found will require you to abandon every remaining intuition about what motion means at the quantum level, because at that level motion is not what you think it is. Particles do not travel from one place to another along paths. They travel along every path simultaneously, and it is in the mathematics of that simultaneous exploration of all possible paths that the speed of light emerges, not as a limit, not as a barrier, but as the natural consequence of what it means for a quantum amplitude to contribute to observable reality. The answer is not that faster than light paths are forbidden. The answer is that faster than light paths cancel themselves out of existence before they can matter. Phần 4, 7 hoàn thành. Số từ phần này 2750 từ tổng số, từ tích lũy 9300 từ phần tiếp theo. Phần 5 sẽ đi vào Richard Feynman tại Princeton năm 1939, cuộc khủng hoảng của Quest và bài toán vô cực tích phân đường và tổng lịch sử. Tại sao các con đường nhanh hơn ánh sáng tự triệt tiêu nhau trong tổng? Lượng tử sơ đồ Feynman và hạt ảo và kiểm chứng 3D với độ chính xác 1/1000 tỷ. Nói OK để tiếp tục. OK 845. Richard Feynman arrived at Princeton University in the autumn of 1939, carrying a reputation that made his professors simultaneously delighted and slightly uneasy. He was 21 years old, the son of a uniformed salesman from Far Rockaway, Queens, a borough of New York City that produced few theoretical physicists. He had grown up fixing radios in the neighborhood, developing an instinct for how things actually worked, rather than how textbooks described them working. He had taught himself calculus before his high school offered it. He had arrived at MIT as an undergraduate and proceeded to solve problems that left faculty members pausing to check his work, not because they suspected errors, but because his methods were so unconventional that verification required translating his approach into the standard language of physics before comparison was possible. At Princeton, his doctoral advisor was John Archibald Wheeler, one of the most imaginative theoretical physicists of the century. Wheeler had a gift for identifying the questions that mattered and the people capable of answering them. He recognized in Feynman something he rarely encountered. Not merely exceptional mathematical ability, not merely physical intuition, though Feynman had both in abundance. Wheeler recognized a physicist who experienced the equations differently than other physicists. Where most theorists saw symbols and relationships, Feynman saw processes and pictures. Where others calculated, Feynman visualized. Where others followed established methods, Feynman invented new ones because the established methods failed to show him what he needed to see. This visual imagination, this insistence on understanding physics as something you could picture, rather than merely compute, would eventually crack open one of the deepest mysteries in all of science. Not just what happens when objects approach light speed, which Einstein had already answered with extraordinary completeness, but why the universe enforces this limit with such absolute mathematical inescapable precision, why the barrier exists at all, why it is located at exactly this particular speed rather than some other value. The answer Feynman found did not add new constraints to physics. It revealed that the light speed limit was never a constraint at all. It was a consequence, an inevitable outcome of the deepest rules governing how physical reality is constructed from quantum mechanical ingredients. And to understand what he found, you must first understand the problem he was trying to solve. Quantum electrodynamics, the theory describing how light and matter interact at the quantum level, was in a state of quiet crisis when Feynman began his graduate work. The basic framework had been established in the late 1920s and 1930s by Paul Dirac Werner, Heisenberg, Wolfgang Pauli, and others. They understood that charged particles like electrons interact by exchanging photons, the quantum particles of the electromagnetic field. They had equations describing these interactions. The equations were relativistically correct, incorporating special relativity in the way Dirac's brilliant work had shown was necessary. The framework seemed sound in its foundations, but when physicists tried to use these equations to calculate anything beyond the simplest possible processes, the calculations produced answers that were not merely wrong. They were infinite, not very large, not larger than expected, infinite. Precisely, exactly, mathematically infinite, the kind of infinity that makes an equation useless because it says nothing useful about the physical world. Consider the most elementary question imaginable. What is the energy of a single electron sitting alone in empty space, not interacting with anything, simply existing? The electron carries an electric charge. That charge generates an electromagnetic field extending through space around it. That field contains energy. The electron interacts with its own field, and this self-interaction affects the electron's properties. When physicists calculated this self-energy using quantum electrodynamics, integrating the field's energy contributions over all of space, the answer came out infinite. Not large, infinite. Calculate the probability that a photon scatters off an electron. Infinite correction terms appear. Calculate the precise magnetic properties of the electron. Infinite. Calculate any quantity that involved what physicists called loop diagrams, processes where particles created themselves and their antiparticles momentarily before annihilating again, and infinities appeared without exception, without fail, with maddening consistency. The theory seemed to be telling physicists that every electron in the universe had infinite energy, infinite mass, infinite charge, that the probability of any scattering event was infinite, that the magnetic moment of the electron was infinitely larger than any finite measurement could ever reveal. Obviously, none of this was true. Electrons had measured finite masses and charges and magnetic properties. Scattering events occurred at measurable finite rates. Something was catastrophically wrong. Some physicists concluded that quantum electrodynamics was simply broken, that reconciling quantum mechanics with special relativity was perhaps impossible, and that entirely new theoretical foundations were required. The crisis persisted throughout the late 1930s and into the war years, unresolved, uncomfortable, a fundamental failure at the heart of the most successful physical theory anyone had constructed. Feynman spent the war years at Los Alamos, contributing to the Manhattan Project while carrying the theoretical puzzle with him. He worked on implosion calculations during the day. He thought about quantum electrodynamics at night. He was 24 years old, 25, 26, doing the most morally complex work of his life, while his mind remained elsewhere, wrestling with infinities and wondering what they were trying to say. When the war ended and he moved to Cornell University, he had the time and the distance from classified work to attack the problem directly. And he attacked it in the way he attacked every problem, by discarding the established methods entirely and finding a new way to see what was actually happening. Feynman's breakthrough was a completely new way of formulating quantum mechanics itself. The standard approach developed by Erwin Schrödinger and Werner Heisenberg in the 1920s described quantum systems through wave functions evolving according to differential equations. These methods were mathematically rigorous and produced correct predictions, but they were abstract in a way that made physical visualization difficult. The wave function for a particle existed in a mathematical space that had no direct geometric interpretation. Following its evolution through time required solving differential equations that became intractable for any realistic multiparticle system. Feynman proposed something that sounded at first hearing like the description of a fever dream. When a quantum particle travels from point A to point B, it does not follow a single path. It follows every possible path simultaneously. Not metaphorically, not approximately. Every single path that connects the 2 points in the entire history of paths that could conceivably connect them contributes to the particle's behavior. Paths that go directly from A to B, paths that detour slightly, paths that curve dramatically through space, paths that loop back on themselves, paths that spiral outward to the edge of the observable universe before returning, paths that travel backward in time. Every path, all of them, simultaneously, always. This sounds like the description of a system with no predictive power whatsoever. If everything happens, how do you calculate anything? If every path contributes, how does a particle ever end up in a specific location rather than being equally probable everywhere? The answer lies in how the contributions combine. Each path is assigned a complex number called a probability amplitude. A complex number has both a magnitude, telling you how strongly that path contributes, and a phase, a direction in the complex plane, telling you how that path's contribution aligns with contributions from other paths. The amplitudes from all possible paths are added together, and the result determines the probability of any particular outcome. The crucial mechanism is interference. Two paths whose amplitudes point in opposite directions in the complex plane cancel each other. Two paths whose amplitudes point in the same direction reinforce each other. Paths cancel and reinforce exactly as waves cancel and reinforce because amplitudes are wave-like mathematical objects. Now consider what happens when you sum over all possible paths between 2 points. Paths that wander wildly through space, taking enormous detours through distant regions, accumulate rapidly changing phases as you vary them slightly. Nearby wild paths point in completely different directions in the complex plane. They cancel each other almost perfectly. Their collective contribution to the total amplitude is negligible. Paths that stay close to the classical trajectory, the path that classical physics would predict for a particle following Newton's or Einstein's laws, have a special property. Small variations around this path produce only small changes in phase. Nearby, classical paths all point in roughly the same direction in the complex plane. They reinforce each other rather than cancelling. Their collective contribution dominates the total amplitude. This is how classical behavior emerges from quantum weirdness. The particle does not follow the classical path because some rule forces it to. The particle explores every path simultaneously. But the wild paths cancel each other into irrelevance, while the classical path and its near neighbors reinforce each other into dominance. The particle is most likely found near where classical physics predicts, not because quantum mechanics agrees with classical mechanics, but because quantum mechanics, when applied correctly and completely, produces classical mechanics as a consequence of the interference mathematics. Feynman demonstrated that this path integral formulation summing probability amplitudes over all possible paths was mathematically equivalent to the Schrödinger equation approach. Both frameworks make identical predictions for every possible experiment. The physics is the same, but the picture is utterly different, and it is in the picture that the truth about the light speed limit becomes visible. The contribution each path makes to the total amplitude is determined by a quantity called the action calculated by integrating a function called the Lagrangian along that path. The Lagrangian encodes the physics of the system, the kinetic energy, the potential energy, the interactions between particles. For a free relativistic particle, the Lagrangian has a specific form dictated by special relativity, and light speed appears in this form as the fundamental parameter relating spatial and temporal dimensions of the path. When a path includes a segment where the particle moves faster than light, something specific and decisive happens to the action calculated along that segment. The action becomes imaginary, not small, not negative. Imaginary in the precise mathematical sense of involving the square root of -1, a complex number whose phase is rotated exactly 90 degrees from the real axis. And when the action is imaginary, the phase of the probability amplitude changes not smoothly and continuously as the path varies, but infinitely rapidly. Infinitely rapid phase variation means something specific and devastating when you sum over all nearby paths. A path with infinitely rapidly varying phase has no coherent relationship with any of its neighbors. Neighboring paths point in completely random directions in the complex plane. They cancel each other not approximately, but exactly, with absolute mathematical precision. A superluminal path contributes exactly 0 to any observable quantity. Not approximately 0, not negligibly small, exactly 0. The cancellation is perfect. The contribution is absent. The superluminal path exists in the mathematical sum but produces no physical effect whatsoever because it cancels itself and every nearby path into total annihilation before any trace of its existence can reach the final amplitude. This is the quantum mechanical reason nothing travels faster than light. The universe does not post speed limit signs. It does not employ enforcement mechanisms. It does not exert forces that prevent superluminal motion. It simply constructs reality through a summation process in which superluminal contributions cancel themselves out of existence with mathematical precision before they can influence anything observable. Faster-than-light paths do not contribute to reality because they destroy each other before reaching it. Einstein showed that infinite energy would be required to accelerate a massive particle to light speed. This was the geometric face of the barrier, written in the language of spacetime curvature and the Lorentz transformation. Feynman revealed the quantum mechanical face. The barrier is not imposed from outside. It emerges from within, from the deepest rules governing how probability amplitudes combine. There is no separate constraint requiring enforcement. The quantum mathematics automatically, inevitably perfectly eliminates superluminal contributions from every calculation. Asking how to travel faster than light, Feynman's formulation reveals, is not like asking how to overcome a very strong force. It is like asking how to make a number contribute to a sum after it has already cancelled to exactly 0. The question has no answer, because the premise assumes a contribution that does not exist. Feynman developed his famous diagrams as practical tools for implementing these ideas in actual calculations. Julian Schwinger at Harvard and Shinichiro Tominaga in Japan were simultaneously developing the same physical theory through different mathematical approaches. All three shared the Nobel Prize in Physics in 1965 for their work, but it was Feynman's diagrams that transformed quantum electrodynamics from a theoretical framework accessible only to specialists into a practical calculational tool that graduate students could learn and apply. A Feynman diagram looks deceptively simple. Lines represent particles propagating through spacetime. Vertices, points where lines meet, represent interactions where particles are created, absorbed, or exchanged. Time conventionally flows from left to right or bottom to top. Space extends in the perpendicular direction. An electron moving through space appears as a straight line with an arrow indicating the direction of travel through time. A photon, the quantum of the electromagnetic field, appears as a wavy line. An electron emitting a photon appears as an electron line with a wavy branch departing from a vertex, the electron continuing beyond, with altered momentum, having transferred some energy and momentum to the departing photon. Two electrons repelling each other appears as two roughly parallel electron lines connected by a wavy photon line, the exchanged photon carrying momentum from one electron to the other, deflecting both. Each diagram corresponds to a precise mathematical expression through a set of rules called Feynman rules. Every line has an associated mathematical factor called a propagator. Every vertex has an associated factor called a coupling constant. Multiplying these factors together and integrating over the appropriate variables yields the amplitude for that particular process. adding amplitudes from all diagrams contributing to a given process and taking the absolute square yields the probability. The procedure sounds mechanical, and in many ways it is, which was precisely the point. Feynman wanted calculations that could be done systematically, that could be checked, that could be extended to higher precision by including more diagrams without requiring brilliant insight at every step. He succeeded beyond any reasonable expectation. Calculations that had consumed years of expert labor before 1948 became routine exercises for advanced graduate students after the Feynman rules were established. But the diagrams also illuminate something physically important about the nature of the interactions they encode. The photons exchanged between electrons in these diagrams are called virtual photons. They differ from real photons in a fundamental way. Real photons, the ones that travel across space and enter your eye and trigger your visual system, satisfy a strict relationship between energy and momentum inherited from their zero mass. A real photon with a given energy must have a precisely corresponding momentum. This constraint is called the mass shell condition. Virtual photons are not constrained this way. They can carry any combination of energy and momentum, including combinations that would be physically impossible for real photons. A virtual photon can have more momentum than its energy permits for a real particle. It can have less. It can have negative energy in a certain technical sense. It exists only as an internal line in a Feynman diagram, never as an observed particle in the real world, and the freedom it possesses in the mathematical description enables the calculation of forces and interactions that real particles could not mediate. When critics pointed out that virtual particles seem to violate conservation laws and physical constraints, Feynman explained that this was a misunderstanding of what virtual particles are. They are not physical objects briefly existing in the real world between measurements. They are mathematical devices encoding how fields mediate forces. The impossible energies and momenta appearing in internal lines cancel out in the final sum. Observable quantities, the things experiments can actually measure, always respect conservation laws and physical limits, including the speed of light. This clarification carries a profound implication for the question of superluminal motion. Virtual particles can appear to travel faster than light within the intermediate steps of a Feynman diagram calculation. An internal photon line can connect two vertices in a way that, naively interpreted geometrically, would require faster than light propagation between them. This is permitted in the mathematics. It contributes to the calculation, but observable outcomes, the actual predictions of the theory that can be compared against measurement, never permit faster than light information transfer. The superluminal contributions from virtual particles combine with each other, and with subluminal contributions in the sum over all diagrams such that the final results always respect causality. The virtual internals can be superluminal. The physical externals never are. The mathematics ensures this without additional assumptions, without extra rules, without enforcement mechanisms. It is built into the structure of how amplitudes combine. The experimental confirmation of quantum electrodynamics has reached a level of precision that makes the word confirmation seem almost inadequate. The most dramatic test involves a quantity called the anomalous magnetic moment of the electron, often denoted as G-2 divided by 2, a dimensionless number representing the tiny deviation of the electron's magnetic properties from the value predicted by the simplest version of Dirac's equation. Quantum electrodynamics predicts corrections to this value arising from the electron's interaction with virtual photons in its own electromagnetic field. The electron briefly emits and reabsorbs virtual photons, momentarily becoming surrounded by a cloud of fleeting quantum activity. This cloud modifies the electron's magnetic moment by a precisely calculable amount, including more Feynman diagrams, more loops, more virtual particle interactions, produces more precise predictions. Physicists have computed these corrections to extraordinary depth, including contributions from diagrams containing up to 5 virtual photon loops. The calculation requires evaluating tens of thousands of individual Feynman diagrams, each contributing a specific numerical value to the final sum. The total theoretical prediction involves over 10,000 terms computed with the help of computers running symbolic algebra programs for months. The result, compared to the most precise experimental measurement ever performed, agrees to better than 1 part in 1 trillion. 1 part in 1 trillion. If you measured the circumference of Earth roughly 40 million meters to 1 part in 1 trillion precision, your measurement would be accurate to within 40 micrometers, the width of a human hair. Quantum electrodynamics achieves this level of agreement between theory and experiment, not for a simple property of a simple system, but for a quantum mechanical quantity, involving the interaction of a charged particle with the quantum vacuum surrounding it. No other theory in the history of science has been tested so precisely and confirmed so completely. Quantum electrodynamics is not approximately correct. It is exactly correct to the limits of our ability to measure and calculate, and every one of its predictions embedded in a theoretical framework where faster-than-light contributions cancel themselves out of every observable quantity by mathematical necessity, has been verified beyond any reasonable doubt. The standard model of particle physics extends Feynman's quantum electrodynamics to encompass all known fundamental particles and forces except gravity. It describes quarks and gluons, the constituents of protons and neutrons. It describes the W and Z bosons carrying the weak nuclear force. It predicts the Higgs boson detected at CERN in 2012, with properties matching theoretical predictions to remarkable precision. The entire framework rests on the path integral formulation and the principle of summing over all possible histories. Every particle in the standard model obeys the speed of light limit, not because the model imposes this limit as an additional constraint, because the mathematical structure of relativistic quantum field theory automatically inevitably produces it as a consequence of requiring that the theory remain logically consistent. Attempts to construct quantum field theories permitting superluminal propagation do not merely produce wrong predictions. They produce theories where probabilities become negative, where conservation laws fail, where the mathematics refuses to cohere into anything that could be called a physical theory. The only quantum field theories that work, the only ones that produce finite, positive, sensible predictions that match measurements, are theories where the speed of light emerges as the maximum propagation speed for all fields, not imposed, emergent, a consequence of logical consistency rather than an additional assumption. Quantum entanglement presents what appears at first and second and even third inspection to be a challenge to everything Feynman's framework implies about the universality of the speed limit. Measure one particle from an entangled pair, and you instantly know something about its distant partner, regardless of the separation between them. The correlation appears the moment you measure, not after a light speed delay, not after any delay at all. Einstein called this spooky action at a distance and found it deeply troubling, suspecting it proved quantum mechanics was incomplete, that hidden variables must exist beneath the quantum description to explain these correlations through local mechanisms. Bell's theorem, developed by John Bell in 1964 and tested experimentally from the 1970s onward through increasingly sophisticated experiments, culminating in the loophole-free tests of 2015, demonstrated that Einstein was wrong. The correlations between entangled particles are stronger than any local hidden variable theory can produce. The entanglement is real. The non-locality is genuine. The correlation truly is instantaneous. And yet no information travels faster than light. This is not a paradox with a clever resolution. It is a precise mathematical result. When you measure your local particle, you get a random result, spin up or spin down with equal probability. Your distant partner's result is determined the moment yours is, but your partner also sees only randomness from their perspective. To discover that your results are correlated, that whenever you got spin up, they got spin down, you must compare your measurements. That comparison requires ordinary communication, sending a signal, making a phone call, exchanging data over some physical channel, and that channel operates at light speed or slower. The correlation exists instantly. Knowledge of the correlation travels at light speed. These two statements are simultaneously true, and together they ensure that entanglement cannot be exploited to send information faster than light. Physicists have proven this mathematically through the no communication theorem. The theorem demonstrates that quantum mechanics preserves causality despite its non-local correlations, because non-local correlations without the ability to control them are indistinguishable from randomness to any local observer. Quantum mechanics walks right up to the edge of violating causality. Its instantaneous correlations reach across arbitrary distances in zero time. And then, it stops precisely at the boundary where an actual violation would begin because the correlations are uncontrollable. They are real but random. Real randomness, uncontrollable randomness. Randomness that you cannot steer or select or encode information into is causally inert. The path integral formulation explains why this happens. Superluminal contributions to the quantum sum cancel exactly. What remains respects causality. The instantaneous correlations of entanglement are not superluminal signals. They are non-local correlations in a universe where the underlying quantum amplitude structure ensures that such correlations can never be harnessed for signaling. The mathematics builds in the protection at the foundation level. No exploitation is possible because the exploitation route leads to exactly cancelling amplitudes. Feynman understood all of this with unusual clarity. He was fond of saying that anyone who claims to understand quantum mechanics does not understand quantum mechanics, by which he meant not that quantum mechanics was mysterious in principle, but that its correct understanding requires abandoning intuitions so deeply embedded in human cognition that the abandonment feels like losing something essential. The path integral picture makes explicit what those intuitions miss. Reality is not constructed from particles following paths. It is constructed from amplitudes summing over all paths. The paths that survive this summation, the ones that contribute to observable reality, are the subluminal ones. The superluminal ones cancel. Not because of rules, because of mathematics, because of what it means for complex numbers to add. And this means something that should settle permanently in your mind: the question of whether the light speed barrier might someday be circumvented. It will not. Not because we lack sufficiently advanced technology, not because we have not yet discovered the right physics, not because the barrier is very strong and requires enormous force to break, but because the barrier is the shape of the mathematics from which reality is constructed. To break it would require not a more powerful engine, but a different universe, one built from different quantum mechanical foundations, one where amplitudes combine differently, one where the path integral structure allows superluminal contributions to survive the summation rather than cancelling perfectly. Our universe is not that universe. Our universe is the one where the mathematics works out exactly as Feynman showed, where everything that can be observed is built from subluminal amplitudes, where light speed is not the fastest thing permitted, but the speed at which the underlying quantum structure transitions from contributing to cancelling. The barrier is not a wall, it is the edge of the territory in which physical reality exists. 0848. The speed of light has nothing to do with light. This statement, which would have seemed like obvious nonsense to any physicist working before 1905, is now understood to be one of the most precise descriptions of physical reality available to us. The constant we call light speed, the number 299,792 kilometers per second that appears in Maxwell's equations and Einstein's relativity and Feynman's path integrals, is not a property of photon. It is a property of spacetime. It is the rate at which cause produces effect anywhere in the universe, under any circumstances, through any mechanism, involving any particles or fields or forces whatsoever. Photons travel at this speed because they are massless. Any massless particle must travel at exactly this speed. Not approximately, not nearly, but exactly, because massless particles have no rest frame. You cannot catch up to a photon because catching up would require occupying a frame in which the photon is stationary, and no such frame exists within the geometry of spacetime. The photon is not moving through spacetime. The photon is a disturbance propagating along a null geodesic, a path through spacetime that has zero interval length, a trajectory that exists at the boundary between the time-like and space-like regions of the causal structure. Remove photons entirely from your conception of this constant. Imagine a universe with no electromagnetic radiation whatsoever, no light, no radio waves, no gamma rays, nothing. The constant would still exist, Gravity would still propagate at exactly this speed. The strong nuclear force mediated by gluons, which are also massless, would still operate at exactly this speed within atomic nuclei. The Higgs field disturbances would propagate at exactly this speed. The speed exists independently of the particles that happen to travel at it. It is the geometry talking, not the particles. The proper name for this constant, the name that captures what it actually describes, is the speed of causality. It is the maximum rate at which any cause can produce any effect anywhere in the cosmos. And understanding it as causality, rather than as light, transforms how you see everything that follows from it. Causality, stripped to its barest essence, is the relationship between events where one influences another. A star explodes. The shockwave expands outward. Planets in its system are sterilized. The relationship between the explosion and the sterilization is causal. One preceded and produced the other. This seems so elementary that examining it carefully feels almost foolish, and yet the full implications of what causality requires have taken humanity centuries to appreciate. For one event to causally influence another, information about the first event must reach the location of the second event before the second event occurs. The window shattering cannot precede the rock's arrival. The patient cannot respond to medicine before it is administered. Effect cannot outrun cause because effect is produced by cause, and production requires the causing information to propagate from cause to effect. This propagation has a maximum speed, the speed of causality, and this maximum speed creates a geometric structure in spacetime that governs every physical relationship in the universe. Picture yourself at a specific location in space, at a specific moment in time. Now imagine a cone extending outward from your position into the future, expanding at the speed of light in every spatial direction simultaneously. This is your future light cone. Every event that lies within this cone, every location in space, reachable by a light beam leaving your position at this moment, can potentially be influenced by what you do right now. Every event outside this cone is beyond your reach. No action you take, no signal you send, no force you exert can affect events outside your future light cone, because reaching them would require information to travel faster than the speed of causality. Now imagine a second cone extending backward into the past, contracting toward your position at the same rate. This is your past light cone. Every event that lies within this cone, every location in space from which a light beam could have reached your current position by this moment, may potentially have contributed to your current state. Every event outside your past light cone is causally irrelevant to your existence right now, because information from those events has not yet had time to reach you. These two cones together, the future cone and the past cone, define your causal relationship with the entire universe at this moment. Inside the future cone lies everything you can affect. Inside the past cone lies everything that could have affected you. Outside both cones lies the vast majority of space-time causally disconnected from your present moment, neither reachable by you nor capable of reaching you. Existing in a perpetual present, neither your past nor your future, but simply elsewhere. The technical term for events outside both light cones is space-like separation, and space-like separation carries a property that should arrest you completely when you first encounter it. For space-like separated events, different observers disagree about which event happened first. Observer A, moving at one velocity, calculates that event X occurred before event Y. Observer B, moving at a different velocity, calculates that event Y occurred before event X. Observer C, moving at yet another velocity, calculates that both events occurred simultaneously. All three observers are correct. All three measurements are valid. There is no objective temporal ordering for space-like separated events, because temporal ordering only has objective meaning for events that can causally influence each other. This is not a measurement error. This is the actual structure of space-time, revealing that simultaneity, the notion that events happen at the same time, is not a universal absolute fact, but a relationship that depends on the observer's state of motion. For causally connected events, the ordering is absolute. Every observer agrees that cause precedes effect. For causally disconnected events, the ordering is relative observer dependent, genuinely ambiguous in the deepest physical sense. The speed of light draws the boundary between these two categories. It defines which events can causally connect and which cannot. It determines where objective temporal ordering ends and observer-dependent temporal ordering begins. It is the geometrical parameter that gives time its directionality for causal processes, while leaving the temporal ordering of causally disconnected events undefined. This is why faster-than-light travel is not merely prohibited, but paradoxical. If you could reach a space-like separated event, you would be establishing a causal connection between two events whose temporal ordering is observer-dependent. For some observers, you would arrive before you departed. For others, you would arrive after. No consistent causal narrative could be constructed. The paradoxes that arise are not philosophical puzzles awaiting clever resolution. They are symptoms of a logical structure that has broken down entirely. The mathematics of spacetime does not contain a coherent description of what superluminal causation would look like, because the concept requires temporal ordering where none exists. Spacetime geometry encodes the light speed limit not as a constraint appended to an otherwise unconstrained structure, but as the fundamental parameter defining the geometry itself. The interval between two events, the spacetime equivalent of distance, is calculated by a formula that combines spatial separation and temporal separation through the speed of light. The interval equals the speed of light squared multiplied by the time separation squared minus the spatial separation squared. This interval has a property that astonished physicists when Einstein first derived it, and continues to seem remarkable no matter how many times it is encountered. The interval is invariant. Every observer, regardless of their velocity, calculates the same interval between any two events. They disagree about the spatial separation, they disagree about the temporal separation. But the specific combination of these quantities that constitutes the interval remains identical for all observers. It is the one quantity about which the universe does not argue. When this invariant interval is positive, the two events are time-like separated. Their temporal separation dominates their spatial separation. A signal traveling slower than light can connect them. Their temporal ordering is absolute. When the interval is negative, the two events are space-like separated. Their spatial separation dominates their temporal separation. No signal traveling at or below light speed can connect them. Their temporal ordering is observer-dependent. When the interval is exactly zero, the two events are light-like separated. A signal traveling at exactly light speed connects them. They lie on each other's light cones. This is the boundary, the causal margin, the precise edge where absolute temporal ordering ends. The speed of light appears in the formula for this interval not as an incidental constant that could be replaced by any other value without consequence, but as the fundamental geometric parameter that defines the shape of spacetime. Change the speed of light, and you change the geometry of the universe. You change which events can causally influence which others. You change the shape of every light cone. You change the causal structure of all of physical reality. In this sense, the speed of light is less like a speed and more like the conversion factor between the time axis and the spatial axes in spacetime geometry. Just as the Pythagorean theorem uses a specific geometric relationship between spatial dimensions, the spacetime interval formula uses light speed to relate the temporal dimension to the spatial dimensions. Light speed is the slope of the light cone in the four-dimensional diagram of spacetime. It is the angle at which causality propagates through the unified fabric of space and time. Physicists who work with these ideas daily often use units where the speed of light equals exactly 1. In these units, 1 second of time is equivalent to 29979, 2 kilometers of space, because the conversion factor between temporal and spatial units is light speed. Setting it equal to 1 is not an approximation. It is a choice of units that reveals the underlying unity of space and time more clearly than the familiar metric units that happen to make the conversion factor a large number rather than unity. In these natural units, the interval formula simplifies to time squared minus space squared. The speed of light vanishes from the formula not because it is unimportant, but because it has been absorbed into the unit system. Its influence pervades every relationship in the simplified equations. You see it everywhere precisely because you defined it away from view. Gravity obeys the speed of causality. with the same absolute precision as electromagnetism, and the detection of gravitational waves in 2015 transformed this from a theoretical prediction into a measured, verified, observed fact. Einstein predicted gravitational waves in 1916 almost immediately after completing general relativity. His field equations, describing how the curvature of spacetime responds to the presence of mass and energy-permitted wave solutions. Just as accelerating electric charges produce electromagnetic waves, accelerating massive objects should produce ripples in spacetime itself, distortions propagating outward at exactly light speed, compressing space in one direction while expanding it in the perpendicular direction, oscillating between these two configurations as the wave passes. The detection challenge was staggering. Gravitational waves are real physical distortions of space-time, but their amplitude by the time they reach Earth from any astrophysical source is almost incomprehensibly small. A gravitational wave powerful enough to produce a strain, a fractional change in length of 1 part in 10 to the 21st power, requires 2 neutron stars, or black holes, 2 objects containing more mass than the Sun compressed into, volume smaller than a city, spiraling toward each other and colliding with the energy release of more stars than exist in most galaxies. The LIGO observatories, the Laser Interferometer Gravitational Wave Observatory, consisting of 2 facilities located in Louisiana and Washington State, each containing laser beams bouncing between mirrors separated by 4 kilometers, were sensitive enough to detect length changes smaller than 1,000th the diameter of a proton. This precision maintained across facilities separated by 3,000 kilometers represented decades of technological development and required isolation from vibration at a level that staggers the imagination. On the 14th of September 2015, both facilities detected a signal that matched the predicted signature of 2 black holes merging. The black holes, one approximately 36 times the mass of the Sun, and the other approximately 29 times solar mass, had been spiraling toward each other for billions of years, and collided approximately 1.3 billion light-years from Earth. In the final fraction of a second of their in-spiral, they radiated more energy and gravitational waves than all the stars in the observable universe combined, radiate in electromagnetic radiation during the same interval. The signal arrived at the Louisiana facility first, then at the Washington facility 7 milliseconds later, a delay consistent with a wave traveling at light speed across the 3,000-kilometer separation between the 2 detectors. From this and subsequent detections, physicists measured the propagation speed of gravitational waves and found it to match light speed to better than 1 part in a million billion. Gravity and electromagnetism travel at exactly the same speed, not approximately, not coincidentally, exactly. Because both are mediated by massless particles, gravitons and photons respectively, and all massless particles travel at the speed of causality. The speed of light is not a speed that light happens to travel. It is the speed at which space-time itself propagates changes in its own curvature, the rate at which the universe updates its gravitational configuration in response to the motion of mass. When the Sun moves, the gravitational field of the solar system does not instantaneously reconfigure. It updates outward at light speed. If the Sun was suddenly removed from existence, Earth would continue in its orbit for 8 minutes, feeling the gravitational influence of a star that no longer existed before the updated field configuration reached us. Gravity, like light, is bound by causality. Black holes are the ultimate expression of what happens when the speed of causality becomes the determining factor in the structure of a region of space-time. A black hole forms when enough mass is compressed into a small enough volume that the escape velocity at the surface reaches light speed. Below this surface, the event horizon, not even light can escape. Since nothing travels faster than light, nothing escapes. The interior of a black hole is permanently and completely causally disconnected from the exterior universe. The event horizon is not a physical surface. No membrane exists there, no wall, no barrier that an infalling observer would feel or notice at the moment of crossing. It is a causal boundary, a surface in space-time defined entirely by the geometry of light cones. At the event horizon, light cones that normally open toward the future, pointing upward in the spacetime diagram, tilt over exactly to the horizontal. Light emitted at the horizon cannot escape, but it cannot fall inward either. It is trapped, propagating forever along the horizon itself, making no progress outward, but equally unable to progress inward. Just inside the horizon, light cones tilt past horizontal, pointing partially inward. A particle inside the horizon, even one traveling at the speed of light in the outward direction, is carried inward by the geometry of spacetime. Outward is no longer a direction that leads to the exterior universe. Outward, inside an event horizon, leads toward the singularity. The singularity is not a location in space. It is a moment in the future of every interior trajectory. You cannot avoid it any more than you can avoid tomorrow. No engine, no matter how powerful, can point you away from it. It is simply where time ends inside a black hole, the future boundary of space-time within the horizon. This is the speed of causality expressed at its most extreme. The event horizon is not a wall the light speed limit places in space. It is a boundary the light speed limit carves in space-time itself, defining a region from which no causal influence can ever emerge. Anything that happens inside an event horizon stays inside an event horizon, not because of some cosmic information security policy, but because the causal structure of space-time in that region points everything, including the future itself, toward the singularity. Hawking radiation, the quantum mechanical process by which black holes slowly emit thermal radiation over astronomical timescales, represents the one way in which information might eventually escape from a black hole's gravitational influence. Whether and how this process preserves information about what fell into the black hole remains one of the deepest unsolved problems in theoretical physics, lying at the intersection of quantum mechanics and general relativity. But Hawking radiation does not violate the causal boundary of the event horizon. It is generated at the horizon through quantum processes and radiates outward from that boundary, not from the interior. Black holes thus stand as the most extreme monuments to the speed of causality in the observable universe. They are regions where the geometry of spacetime, shaped by the accumulation of mass beyond a critical threshold, creates permanent and absolute causal disconnection. They are sealed not by any force, not by any material, but by the shape of time itself, curved inward, past the point of return, by gravity operating at the speed at which gravity propagates. The observable universe has a boundary, and that boundary is defined entirely by the speed of causality and the age of the universe. Light has been traveling since the universe began approximately 13.8 billion years ago. In that time, the fastest possible signal has covered a specific distance. Events beyond a certain separation from Earth are outside our observable universe, not because space ends there, but because light from those locations has not yet had time to reach us. The universe is causally young. Most of it has not yet had time to communicate with us. The observable boundary, the cosmic horizon, lies approximately 46 billion light-years away in every direction, despite the universe being only 13.8 billion years old. This apparent contradiction resolves when you account for cosmic expansion. The universe has been expanding since the Big Bang. Light that left a distant region 13 billion years ago traveled through space, that was itself expanding as the light crossed it. By the time that light arrives at Earth, the region that emitted it has been carried much farther away by the cumulative expansion. The region is now 46 billion light-years away, even though the light that left it has been traveling for only 13.8 billion years. Beyond our cosmic horizon lie regions that almost certainly contain galaxies, stars, planetary systems, chemistry, and possibly forms of life or intelligence. We have no way to know. No signal from those regions has reached us. No information about them exists within our observable universe. They may be identical in large-scale structure to what we can observe smoothly, extending the patterns of galaxy distribution visible within our horizon, or they may differ in ways we cannot anticipate. We have no access to any evidence either way. The situation becomes more severe as cosmic expansion accelerates. Dark energy, the mysterious component of the universe, whose nature remains among the greatest unsolved problems in cosmology, is driving galaxies apart at an increasing rate. Galaxies beyond a certain distance are receding faster than light speed relative to us, not because they are moving through space faster than light, but because the space between us is expanding on large enough scales in an accelerating universe. The expansion rate between 2 points can exceed light speed, even though no local motion exceeds it. These rapidly receding galaxies have crossed beyond the region from which light will ever reach us in the future. We can still observe the ancient light they emitted billions of years ago, light that was already on its way toward us before their recession speed exceeded the speed of causality. But any light they emit today will never reach us. The expansion carries it away faster than it can approach. They are permanently and irreversibly beyond our causal future horizon. Over the next tens of billions of years, as dark energy continues driving, accelerating expansion, galaxy after galaxy will cross this horizon. The observable universe will become progressively emptier, not because galaxies are being destroyed, but because they are being carried beyond the reach of causal contact. The gravitationally bound local group of galaxies, our Milky Way, the Andromeda Galaxy, and their smaller companions, will eventually merge into a single enormous elliptical galaxy. Everything outside this local group will eventually vanish beyond the horizon, leaving this merged system apparently alone in an otherwise empty cosmos. Astronomers living in this distant future, perhaps 100 billion years from now, will look outward and see nothing. No distant galaxies, no cosmic microwave background radiation, which will have redshifted to wavelengths so long that no conceivable detector could observe them. No evidence of the Big Bang, no evidence of cosmic expansion. They will see a single large galaxy surrounded by apparent emptiness, and may reasonably conclude that the universe is a single island of stars surrounded by infinite void, that nothing exists beyond their galaxy's edge, that the cosmos is tiny and simple and static. The speed of causality will have erased the evidence of cosmic history by placing it beyond any possible horizon. The most consequential facts about the universe's origin and structure will have become permanently inaccessible, not through any process of destruction, but through the simple mathematics of expansion faster than the speed at which information can travel. This is the light speed limit operating at its most cosmological scale, not as an engineering constraint on spacecraft, not as a limit on particle accelerators, but as the fundamental parameter determining which regions of the universe can share information across cosmic time and which are forever sealed off from each other by the geometry of an expanding, accelerating spacetime. The arrow of time, the fact that time flows in one direction from past to future, rather than being symmetric in both directions, connects to the speed of causality in ways that physicists are still working to fully articulate. The fundamental laws of physics are nearly time-symmetric, run most physical processes backward in time, and the result is equally valid physics. A film of billiard balls colliding looks equally plausible forward or backward. A film of an egg spontaneously assembling itself from its scattered components looks absurd because we never observe it, not because physics forbids it in principle. The second law of thermodynamics, the law that entropy increases with time, is the origin of time's apparent directionality in everyday experience. Systems evolve from ordered to disordered states because disordered states are overwhelmingly more numerous than ordered ones, and random evolution among states will almost always lead to more numerous states. But entropy increase requires information to spread. Local low-entropy configurations evolve toward higher entropy by establishing correlations with their surroundings, spreading information outward, entangling themselves with the environment. This spreading of information is bounded by the speed of causality. Correlations cannot establish faster than light speed allows. The thermodynamic arrow of time, the directionality of entropy increase, is constrained by the causal structure that light speed defines. In this sense, the speed of causality is not merely a limit on motion, it is a limit on the rate at which the universe can become more complex, more correlated, more entangled with itself. It determines how quickly order can dissolve into disorder, how quickly structures can establish relationships with their surroundings, how quickly the past can influence the future. The tempo of all physical change everywhere at every scale is set by the fundamental parameter of the geometry of spacetime. We live at a particular moment in cosmic history, when the speed of causality permits stars to burn for billions of years, planets to cool and acquire chemistry life, to evolve through countless generations and intelligence, to develop the capacity to ask why any of this is possible. The specific value of the speed of causality, whatever deeper principles determine it, falls within the range permitting these processes to occur. A significantly lower speed would create a universe where causal influence could spread only across small regions, potentially preventing the large-scale structures that stars and galaxies require. A significantly higher speed would allow so rapid a causal communication between distant regions that the thermal equilibration of the universe might have prevented the formation of structures at all. We observe this particular value because it is among the values that permit observers to exist. This does not explain the value, it merely constrains what values we should expect to find ourselves measuring. The deeper explanation, if one exists, lies in whatever physics underlies the quantum field theory structure that Feynman showed produces light speed as a consequence of how amplitudes combine. That physics, if it exists at a deeper level, remains unknown. What is known is sufficient to be humbling. The universe operates at a specific tempo. Every photon, every graviton, every massless disturbance in any quantum field marches at this tempo without variation or exception. Every massive particle feels the boundary of this tempo as an asymptotic limit approached but never reached. Every causal relationship in the universe is constrained by this tempo. Every light cone, every event horizon, every cosmic horizon, every observable boundary of the universe is defined by this tempo. The speed of light is the heartbeat of the cosmos, and it has been beating since before the first atom formed, since before the first photon existed, since the quantum fields of the early universe first cooled enough to produce the particles we recognize today. It will continue beating long after the last star fades, long after the last black hole evaporates through Hawking radiation into a dilute spray of photons. Long after the last photons themselves redshift to wavelengths longer than the observable universe. The tempo is not a property of the contents of the universe, it is a property of the universe itself. Return for a moment to that hillside outside Florence. Galileo stands in the darkness, with his lantern waiting for a flash of light to cross a valley and return. His assistant waits on the opposite hill, ready to respond the moment he sees the signal. The experiment is elegant, the logic is sound, and the result is nothing. No delay, no measurable transit time. The light appears instantaneous, crossing any earthly distance in zero time detectable by human instruments and human reflexes. Galileo concluded that either light was infinitely fast or moved too quickly for him to measure. He suspected the latter. He was right. But even Galileo, whose mind ranged further than almost any of his contemporaries, could not have anticipated where that suspicion would eventually lead. He was trying to measure the speed of a physical phenomenon the way you might measure the speed of sound or the speed of a river current. He had no way of knowing that he was actually probing the deepest structural parameter of reality itself, that the number he was trying to catch would turn out to be not a property of light, but the conversion factor between time and space in the geometry of the universe, that it would appear in the equations governing gravity, nuclear forces, quantum mechanics, and thermodynamics, that it would define the shape of every causal relationship that has ever existed or ever will exist anywhere in the cosmos. He was standing on a hillside trying to time a pulse of light. He was, without knowing it, asking why the universe has the structure it has. The answer took nearly 4 centuries to assemble. It required Ole Römer watching the moons of Jupiter from Paris and noticing a pattern that everyone else attributed to imperfect orbital models. It required James Clerk Maxwell sitting in a Scottish country house and discovering that electromagnetic waves must travel at a specific speed that happened to match the measured speed of light. It required Albert Michelson and Edward Morley floating an interferometer on liquid mercury and finding nothing where something should have been a null result, so disturbing it threw physics into crisis. It required a 26-year-old patent examiner in Bern to accept two simple postulates and follow their consequences all the way into the collapse of absolute space and absolute time. And it required Richard Feynman to look at the crisis in quantum electrodynamics, the infinities, and the paradoxes, and the broken calculations, and to find a completely new way of understanding what particles actually do when they move through spacetime. Each step revealed that the previous understanding, however successful in its domain, was a partial view of something larger. The speed of light was first a measured quantity, then the maximum speed of electromagnetic disturbances, then the absolute limit enforced by the geometry of spacetime, then a consequence of the quantum mechanical structure of reality itself. At each stage, the question got deeper. At each stage, the answer revealed something more fundamental about why existence has the character it does. Here is what the journey has shown you. 387 years after Galileo stood on that hillside, we know that light travels at 29979, 2 kilometers per second, not because of any property of photons, but because spacetime has a specific geometric structure in which temporal and spatial dimensions are related through this precise conversion factor. We know this because Michelson and Morley found no ether wind, because Einstein derived time dilation and length contraction from two postulates, and the universe confirmed those derivations in GPS satellites and cosmic ray muons and particle accelerators operating daily around the world. We know it because LIGO detected gravitational waves traveling at exactly this speed from a black hole merger, 1.3 billion light-years away, confirming that gravity and electromagnetism share the same fundamental propagation speed because both are mediated by massless fields in the same spacetime. We know that no massive object can reach this speed, not because the universe forbids it the way a law forbids trespass, but because the energy required to reach it is mathematically infinite, which is to say, not merely very large, but a quantity that no physical process in a finite universe can approach without remainder. We know that quantum mechanics explains why this is so at a deeper level than geometry alone can reach, because Feynman showed that superluminal paths contribute exactly zero to the quantum mechanical sum over all histories, cancelling themselves out through perfect destructive interference before they can influence any observable quantity. The barrier is not a wall. It is the edge of the territory in which physical amplitudes survive the summation process. Beyond it, there is nothing to travel to. We know that this limit creates the causal structure of the universe, the light cones that define which events can influence which others, the event horizons that seal black hole interiors from eternal causal contact with the exterior, the cosmic horizon that bounds our observable universe and will eventually swallow the evidence of our cosmic origins as accelerating expansion carries distant galaxies beyond the reach of any possible signal. We know that the arrow of time itself, the directionality that makes the past and the future. The future is shaped by this limit because information can only spread at the speed causality permits, and the spread of information is what entropy increase means at the most fundamental level. This is not a partial picture awaiting completion. It is the most precisely tested and most thoroughly confirmed understanding of any physical phenomenon in the history of science. Quantum electrodynamics predicts the electron's magnetic moment to better than 1 part in 1 trillion, and every digit of that prediction matches experiment. Special relativity has been tested in particle accelerators, atomic clocks, satellite navigation systems, and high-energy astrophysics for more than a century, without a single confirmed contradiction. The speed of causality is known, understood, and verified to a degree that makes doubt about its existence and its absolute character, not a scientific position but an abandonment of the evidence. And yet, knowing all of this, holding the full weight of 4 centuries of discovery and verification, there remains something that the equations cannot capture and that no experiment can measure. You are reading these words in a universe whose fundamental tempo you cannot exceed. The electrochemical signals propagating through your neural tissue as you process these sentences travel at speeds far below light speed, around 100 meters per second for the fastest nerve fibers roughly 3 million times slower than the cosmic limit. The thoughts you are forming right now, whatever response this journey is producing in you, are themselves physical processes bounded by the speed of causality. Your consciousness, whatever it is at the physical level, operates within the same constraints as everything else in the universe. And yet you know about those constraints. You have followed the reasoning from Galileo's hillside to Feynman's path integrals. You have understood, at least in outline, why the barrier exists at the level of quantum amplitude cancellation. You have grasped that the number 299792 kilometers per second is not an arbitrary limit, but the conversion factor between time and space in the geometry of existence. You have done something that no process in the known universe other than conscious thought can do. You have modeled the structure of the universe that contains you. This is not a small thing. The universe is 13.8 billion years old. For 13.8 billion years, the speed of causality has governed every interaction in the cosmos without any part of the cosmos being aware of it. Stars exploded and collapsed under the constraints it imposed. Galaxies formed and merged within the light cones it defined. Black holes sealed themselves behind event horizons it carved in spacetime. And all of this happened in perfect causal order, cause before effect. Information traveling no faster than the geometry permitted the heartbeat of the cosmos, beating steadily through every process without any part of the cosmos knowing that a heartbeat existed. Then, on one small rocky planet, orbiting a middling star in the outer arm of a spiral galaxy, a collection of atoms arranged itself in such a way that it became capable of noticing, of asking, of measuring, of sitting on a hillside with a lantern and wondering how fast the flash would travel, of floating an interferometer on liquid mercury and accepting the disturbing result with intellectual honesty, of imagining what it would mean to chase a light beam, of visualizing particles exploring every possible path through spacetime simultaneously, and realizing that the superluminal paths cancel before they can contribute anything to reality. We are the part of the universe that learned about the speed of light. We are the part of the universe that understood why it exists. We are, as far as we know, the only part of the cosmos that has ever accomplished this. And we did it within the constraints that it imposes using neural processes that obey it within a planet that orbits a star that burns because of it in a universe whose causal structure it defines entirely. The cosmic speed limit confines us absolutely. No human being will ever visit another star system within a human lifetime using any technology that respects the physics we understand. The nearest star beyond our Sun, Proxima Centauri, lies 4.24 light-years away. A spacecraft traveling at 10% of light speed, which exceeds anything we can currently build by many orders of magnitude, would require 42 years to arrive. The travelers would return, if they returned at all, to find everyone they knew aged by nearly a century. The stars are unreachably far, not because we lack sufficient engineering, but because the universe is constructed with a causal structure that makes the distances between stars genuinely fundamentally insurmountably vast relative to human lifetimes. And yet we know the stars are there. We know their distances, their temperatures, their compositions, their ages. We know which ones host planetary systems. We know which of those planets orbit within the habitable zones where liquid water might exist. We have done all of this without leaving our solar system, without any instrument traveling faster than a tiny fraction of light speed, by receiving the photons that stars have been sending toward us for millions and billions of years, and reading in those photons everything the stars are willing to tell. The barrier that prevents us from reaching the stars has not prevented us from knowing them. We are confined to this solar system for all practical purposes of physical travel. We are not confined in our understanding. Our minds operating at speeds 1,000,000 times below the cosmic limit within bodies that will live for less than a century on a planet whose entire history is a brief flicker in the age of the universe, and have reached outward to the edge of the observable cosmos and mapped what they found there. We have reconstructed the first moments of the universe from the microwave glow that remains. We have detected the gravitational ripples from black holes merging 1 billion light-years away. We have understood why the speed of light is what it is at the level of quantum amplitude cancellation, at the level of space-time geometry, at the level of causal structure. This is not despite the barrier. This is within it. This is what the barrier permits. A universe with a finite speed of causality is a universe with an arrow of time, with causal order, with the possibility of memory and anticipation and narrative. A universe where effects follow causes in reliable sequence, where the past can be recorded and the future can be planned. A universe where evolution is possible, because evolution requires that organisms respond to past conditions in ways that affect future survival, which requires that causes precede effects, which requires the causal structure that light speed defines. We exist because the universe has a heartbeat, and we know about the heartbeat because we exist. There is something Feynman said near the end of his life that has stayed with physicists ever since. He was speaking about the mystery of the fine structure, constant, the dimensionless number, governing the strength of electromagnetic interactions, a quantity whose value determines the detailed character of chemistry and biology, and stellar physics, but whose origin no theory has yet explained. He said that all good theoretical physicists put this number up on their wall and worry about it. He was not speaking only about the fine structure constant. He was speaking about the experience of standing at the edge of understanding, knowing precisely how something works, knowing the equations that govern it, and the experiments that confirm those equations, and still not knowing why those equations rather than some others, why this universe rather than some other. The deepest questions in physics are not about mechanisms. The mechanisms are largely known, at least in outline. The deepest questions are about why the mechanisms are what they are. Why is the speed of causality 29979 kilometers per second rather than some other value? Why does the path integral formulation produce exactly cancelling superluminal amplitudes rather than some other behavior? Why is spacetime four-dimensional? Why does it have the specific geometric structure it has? Why does quantum mechanics govern the small scales and general relativity govern the large scales? And why do these two frameworks resist unification in a way that physicists have spent a century trying to resolve? These questions do not have answers yet. They may not have answers in the scientific sense, answers that can be derived from something more fundamental and tested against experiment. They may be the stopping point, the level at which the universe simply is as it is, without further explanation available. Or they may point toward a deeper physics, a more fundamental description of reality from which the specific values of constants and the specific structure of space-time emerge as consequences. We do not know, and not knowing is the honest position. What we do know is that we live in a universe with a specific tempo, a universe where cause precedes effect at every scale, from quantum fluctuations to galactic collisions. A universe where the information content of any region can only spread outward at a bounded rate, creating the light cones that define all causal relationships. A universe where the past is sealed and the future is open, where entropy increases because information spreads, where time has a direction because causality has a speed. We live in a universe that Galileo tried to measure on a hillside and could not, that Roma glimpsed in the drifting eclipses of Jupiter's moon, that Maxwell encoded in 4 equations that unified light with electricity and magnetism, that Einstein rebuilt from the foundation up with 2 postulates and a willingness to follow them wherever they led, that Feynman illuminated from within, showing that the barrier is not imposed on reality, but emerges from the deepest quantum mechanical rules governing how reality is assembled from amplitudes. We live in a universe governed by a heartbeat we can hear but cannot exceed. And the fact that we can hear it at all, that we have learned to measure it and understand it, and trace its implications across 4 centuries of increasingly precise inquiry, is perhaps the most remarkable thing about the small, warm, brief existence we are given within it. The lantern on the hillside could not reveal what it was actually measuring, but we can, and that is enough. That is in the full sweep of cosmic history, an extraordinary thing. A fleeting arrangement of atoms in an unremarkable corner of a middling galaxy looking outward at a universe 13 billion years old and understanding in outline why it works as it does. The light is still traveling. It always is. at 299,792 kilometers per second, unwavering through the cold geometry of spacetime, carrying information about causes to the locations of their effects, maintaining the causal order that makes existence coherent, beating at the tempo that makes time itself possible. It does not know we are listening, but we are.